Have you ever witnessed the truly gigantic megaprojects in the United States? Where blueprints turn into massive structures and where the limits of construction are being redefined. Today, we will uncover the largest megaprojects across the United States, from deep underground to the highest behemoths on planet Earth. These projects will showcase the incredible complexity involved in bringing the country's giants to life.
It's time to travel to New York for the Bayonne Bridge raising project. This development is an extraordinary engineering feat located over the Kill Van Kull Strait, connecting Staten Island, New York, to Bayonne, New Jersey. This project was initiated to address the critical need for modern cargo ships to access the ports of Newark and Elizabeth, New Jersey, which are among the busiest on the eastern seaboard. The original bridge, completed in 1931, had a navigational clearance that was too low for the new generation of ultra-large container vessels introduced with the expansion of the Panama Canal. Completed in 2019, the project successfully raised the bridge's roadway from 151 feet to 215 feet above the water level, while also maintaining the iconic arch design. This adjustment made it possible for ships nearly twice the size of those previously accommodated to pass underneath, significantly increasing the operational capacity and efficiency of the port facilities. The project cost was approximately $1.7 billion, reflecting both its scale and complexity. One of the significant challenges was executing the work without disrupting the heavy vehicular traffic on the bridge, which necessitated innovative construction methods and careful scheduling. In terms of its engineering methodology, the project was notable for its use of the raise the roadway technique. This method involved building a new roadway above the existing one while traffic continued below, and then removing the lower roadway upon completion. Comparing the scale of the Bayonne Bridge project to other engineering projects, its new 215-foot clearance is high enough to accommodate an NFL football field standing on end. The Bayonne Bridge raising faced numerous challenges during its execution, including technical difficulties inherent in working with existing structures, the need to maintain stringent safety standards, and the unpredictable weather conditions over the strait. The project also had to navigate complex regulatory and environmental approvals, coordinating with multiple governmental bodies and community stakeholders to mitigate impacts on the surrounding areas.
Let's take a closer look at the Second Midtown Tunnel project. Located under the Elizabeth River, the Second Midtown Tunnel connects the cities of Norfolk and Portsmouth. Its construction began in 2012 and reached completion in 2016. This project involved building a new two-lane tunnel parallel to the existing Midtown Tunnel, effectively doubling the capacity of this crucial traffic artery. With a cost of $2.1 billion, the construction process for the Second Midtown Tunnel was both innovative and complex. Unlike traditional tunneling methods, this project used an immersed tube technique. Prefabricated tunnel sections, each weighing approximately 16,000 tons, were constructed in a dry dock. These sections were then floated to the site, submerged into a pre-dug trench on the riverbed, and connected to form the tunnel. This method minimized disruption to river traffic and ensured precise alignment of the tunnel sections. The new tunnel not only alleviates traffic congestion, but also enhances safety and travel times for thousands of commuters. In terms of environmental considerations, the project included several measures to mitigate its impact. This included careful monitoring of water quality during construction and the use of innovative techniques to manage and minimize sediment displacement. The Second Midtown Tunnel also features modern safety enhancements, such as advanced ventilation systems, state-of-the-art lighting, and emergency response facilities. These upgrades ensure the tunnel meets contemporary standards for infrastructure resilience and commuter safety. Comparing this project to other major infrastructure endeavors, the Second Midtown Tunnel stands out for its strategic importance in regional connectivity and its use of advanced construction techniques. Let's move over to the next megaproject. Spanning the Hudson River in New York, the Governor Mario M. Cuomo Bridge is a stunning feat of engineering that has reshaped the transportation landscape between Rockland and Westchester counties. Completed in 2018, this impressive structure replaced the aging Tappan Zee Bridge. The project, named after the late New York governor, represents a monumental investment in infrastructure, with a total cost of approximately $4 billion. Constructed over 5 years, the project faced numerous challenges, including maintaining traffic flow on the existing bridge while the new spans were being built parallel to it. The project utilized advanced construction techniques such as floating cranes, one of the largest in the world, known as the I-Lift New York Super Crane, which lifted and placed sections weighing up to 1,200 tons. The bridge stretches approximately 3 miles in length, with each of the twin spans measuring around 1,200 feet at their longest span. These spans are supported by 8 419-foot towers, which are angled outwardly, a design choice that not only provides structural efficiency, but also gives the bridge its visually striking profile. One of the unique aspects of the Cuomo Bridge is its accommodation for various transportation modes. It includes not only 8 traffic lanes, but also a shared-use path for bicycles and pedestrians, featuring 6 scenic overlooks and art installations. In terms of materials, the bridge incorporates more than 220 million pounds of American-made steel and 300,000 cubic yards of concrete. To put the size of the project into perspective, the amount of cable used in the bridge's stay cables could stretch from New York City to Chicago if laid end-to-end. Special features of the bridge include its resilience to extreme weather conditions, designed to withstand the increasing frequency of severe weather events. It is built with corrosion-resistant steel and concrete to ensure a lifespan of over 100 years, significantly improving on the durability of its predecessor. But the most expensive stadium in the United States truly has a staggering construction cost. SoFi Stadium, nestled in the heart of Inglewood, California, represents a pinnacle of architectural grandeur in the realm of sports and entertainment venues. Completed in September 2020, it not only serves as the home for the NFL's Los Angeles Rams and Chargers, but also as a monumental achievement in stadium construction, boasting a final cost of approximately $5.5 billion. One of the hallmarks of its design is the immense, ethereal canopy that covers the stadium and the adjacent plaza. Another standout aspect of the stadium's construction is its below-ground design. To comply with height restrictions near Los Angeles International Airport, the stadium was built into the ground, with its playing field situated 100 feet below ground level. This required extensive excavation work and sophisticated engineering to ensure stability and drainage, contributing significantly to the project's overall costs. Did you know that SoFi Stadium's video board, known as the Oculus, is another example of its unparalleled amenities? This double-sided 4K video board weighs approximately 2.2 million pounds and encircles the interior of the stadium, offering fans a 360-degree viewing experience that is as immersive as it is revolutionary. We have to talk about the Northeast Boundary Tunnel next. This mammoth undertaking, part of the larger Clean Rivers project in Washington, D.C., aims to significantly reduce combined sewer overflows into the Anacostia River, enhancing the river's water quality and complying with federal clean water regulations. The project, which began in 2018, is a critical component in a series of infrastructure improvements designed to modernize the capital's century-old sewer system. Spanning 5 miles in length and located up to 160 feet below ground, the tunnel stretches from the Robert F. Kennedy Stadium to the Rhode Island Avenue NW, with a hefty price tag of approximately $580 million. The construction of the NEBT poses formidable challenges, primarily due to the complexity of drilling a massive tunnel underneath a densely populated urban area. The project utilizes a tunnel boring machine named Chris, a 26-foot diameter behemoth that methodically carves through earth and clay beneath the city. A significant issue the tunnel addresses is the problematic sewer overflow during heavy rainstorms, which historically has led to the pollution of local waterways. The tunnel will capture and store this overflow, transporting it to a treatment facility, thus greatly mitigating the environmental impact and improving the health of the Anacostia River. Throughout the project, DC Water has kept residents informed and involved, addressing concerns ranging from construction noise to local traffic disruptions. Advanced monitoring systems are in place to detect even slight movements of the ground, ensuring that the construction does not affect the integrity of buildings overhead. It's time to travel over to the West Coast for an even more expensive project on our list. The San Francisco-Oakland Bay Bridge Eastern Span replacement was completed in 2013. This project was initiated in response to the vulnerability exposed by the 1989 Loma Prieta earthquake. Its construction showcases a blend of architectural innovation and safety enhancements, with a final cost ballooning to approximately $8.6 billion, far exceeding initial estimates. One of the most striking features of the new Eastern Span is its self-anchored suspension design, a first of its kind for a single tower. This engineering marvel spans 2,047 feet and includes a main cable that loops around the roadway deck, anchoring it securely to itself rather than to the ground. Did you know that over 160,000 miles of wire were used to create the main cable of the bridge? Additionally, the bridge features a 525-foot-tall tower, constructed with 4 steel legs linked by shear link beams designed to flex and dissipate seismic energy. Let's travel over to the next megaproject, the Los Angeles County Metro Purple Line Extension, which is a massive $9.3 billion rail project that's stretching the definition of urban transit development. Extending the Metro Purple Line by 9 miles, this project is not just about adding tracks. It's about seamlessly connecting key sectors of the city, from the skyscrapers of downtown La to the vaunted gates of the University of California. Slated for completion in 2027, the Purple Line extension is currently a hive of activity with over 5,000 workers bustling daily. Building a subway in an area prone to earthquakes demands cutting-edge construction techniques. The team employs advanced tunneling methods, including earth pressure balance machines that delicately burrow beneath the city, ensuring minimal disruption to the surface life and structural integrity of the buildings above. This project solves critical transportation problems in one of America's most congested cities by offering a reliable, high-speed alternative to road travel, effectively reducing traffic and the city's carbon footprint. Once operational, it's expected to serve about 49,000 riders daily. Comparing this to the scale of other megaprojects around the globe, the Purple Line extension. Its budget overshadows the construction costs of the new Wembley Stadium in London, illustrating the monumental investment in public infrastructure and the future of Los Angeles. The project's integration of smart technology systems for maintenance and operation sets new standards for public transportation.
Up next, it's time to investigate the Goethals Bridge. This project is a significant architectural feat in the United States, linking Elizabeth, New Jersey, to Staten Island, New York. The bridge was originally constructed in 1928 and underwent a massive rebuilding project that began in 2014 and concluded with the opening of its eastbound span in 2018. The total project cost was approximately $1.5 billion, highlighting its scope and the investment required to modernize critical infrastructure, designed to replace an aging structure that could no longer efficiently handle modern traffic volumes. The new Goethals Bridge features twin spans, each supporting 3 lanes of traffic, additional shoulders, and a pedestrian and bike pathway that will be completed in a future project phase. One of the most notable methods used was the modular construction approach. Large segments of the bridge were prefabricated off-site and then transported to the location for assembly. This method not only sped up the construction process, but also minimized environmental impact and disruption to the existing traffic. The Goethals Bridge project was a technical challenge involving the installation of 60-foot-tall piers and the lifting of massive 900-ton segments into place. The bridge spans a total length of 1.4 miles, with each of the twin spans stretching approximately 900 feet in their longest span section, requiring precision engineering and construction expertise. One unique aspect of the Goethals Bridge is its focus on sustainability. The project included measures to protect the local marine environment and featured the extensive use of recycled materials. Moreover, the bridge's design incorporates energy-efficient LED lighting and has provisions for future smart transportation technologies. We move over to New York next for the Hudson Tunnel project. This massive project aims to construct a new rail tunnel under the Hudson River, directly addressing the critical need for modernized and reliable rail connections between New Jersey and Manhattan. Currently estimated to cost around $11.6 billion, the Hudson Tunnel project involves constructing a new 2-track rail tunnel, refurbishing the existing century-old tunnel, and making related infrastructure improvements. Upon completion in 2026, it is expected to significantly reduce the risk of severe disruptions in daily commutes and national rail transport. The new tunnel's construction is a complex challenge, requiring sophisticated tunnel boring and under-river drilling techniques to navigate the geological and environmental sensitivities of the Hudson River's underwater terrain. The existing North River Tunnel, which currently serves as the only rail link under the Hudson for Amtrak and New Jersey Transit trains, has been in service since 1910 and was severely damaged during Hurricane Sandy in 2012. The construction of the new tunnel will allow this old tunnel to be closed for repairs without disrupting the critical train services it provides. To understand the scale of the Hudson Tunnel project, consider that the new tunnel will extend about 25 miles under the riverbed, involving millions of cubic feet of excavated earth enough to fill over 1,000 Olympic-sized swimming pools. The project's challenges are immense, from navigating bureaucratic hurdles and securing funding agreements across multiple government entities, to the physical difficulties of urban tunneling.
Moving over to Seattle, it's time to talk about one of the priciest bridges in the country. The Evergreen Point Floating Bridge, also known as the SR 520 Bridge, stretches across Lake Washington to connect Seattle with its eastern suburbs. The bridge holds the title of the world's longest floating bridge, with a construction cost that soared to over $5.8 billion for the entire corridor project, highlighting the massive investment required. The bridge utilizes floating pontoons to support the roadway, a necessity due to the lake's depth and soft lakebed, which make traditional bridge foundations impractical. These pontoons are among the largest ever built, requiring precise engineering to ensure buoyancy and stability. Its construction involved not only the bridge, but also the approach lanes and connecting roads, incorporating extensive environmental mitigation measures to protect the lake's ecosystem. Moreover, the bridge features state-of-the-art safety and traffic management systems, including wind speed sensors and a movable barrier system to optimize traffic flow. Look at the impressive Mercedes-Benz Stadium, home to the Atlanta Falcons and Atlanta United FC. Situated in the heart of Atlanta, this sports and entertainment facility is a testament to modern construction, with a staggering cost of $1.6 billion. The Mercedes-Benz Stadium project broke ground in 2014 and opened its doors in August 2017. Designed by Hawk, the stadium covers approximately 2 million square feet and boasts a seating capacity of 71,000, expandable to 75,000 for major events. The stadium is notable for its innovative retractable roof, which resembles a camera aperture and can open or close in just under 10 minutes. This unique design allows the venue to host events in both open-air and climate-controlled environments, providing flexibility for a wide range of activities. One of the standout features of the Mercedes-Benz Stadium is its 360-degree HD Halo video board, which is the largest of its kind in the world. This massive screen, which spans 1,100 feet in circumference, ensures that every spectator has a clear view of the action, no matter where they are seated. Additionally, the stadium is equipped with cutting-edge technology, including high-speed Wi-Fi and numerous LED displays throughout the venue. Constructing the Mercedes-Benz Stadium was a massive endeavor, requiring the efforts of over 4,000 workers during peak periods. The project faced several challenges, including the complexity of the retractable roof mechanism and the need to integrate numerous sustainable design elements. These sustainable features include a rainwater collection and reuse system, a LEED Platinum certification, and over 4,000 solar panels, making it one of the greenest stadiums in the world. New York's LaGuardia redevelopment project has stepped it up even further. Showcasing a radical transformation at a cost of over $8 billion, this monumental project not only aims to modernize the airport, but also to redefine the passenger experience with cutting-edge design and technology. At the heart of this project is the construction of new terminals, featuring over 1 million square feet of space designed to handle tens of millions of passengers annually. The redevelopment introduces a strikingly innovative dual pedestrian bridge design for Terminal B, allowing planes to taxi underneath. This is a pioneering concept in U.S. aviation, designed to improve taxiway efficiency and reduce gate congestion, a crucial advancement given LaGuardia's limited footprint. Funding this colossal project involves a sophisticated financial structure, including $4 billion for Terminal B alone. Engineering feats within the project include the strategic demolition and phased construction to keep the airport fully operational. Moreover, the incorporation of more than 13,000 square feet of new pedestrian bridges enhances connectivity and streamlines passenger flow, showcasing an impressive blend of functionality and aesthetic appeal.
We have to talk about the 2nd Avenue Subway Megaproject next, located in New York City. Officially part of the Metropolitan Transportation Authority network, this new subway line runs along 2nd Avenue on the east side of Manhattan. The project has been in the conceptual and developmental stages since 1920, but saw its first phase completed and opened to the public on January 1, 2017. Phase 1 of the Second Avenue subway cost approximately $4.45 billion and included 3 new stations with a new terminal at 96th Street. The construction of the Second Avenue subway involved approximately 6,000 workers at various stages, tackling complex urban engineering challenges such as tunneling beneath densely populated areas and avoiding disruptions to the existing utility infrastructures. This necessitated the use of tunnel boring machines, which are sophisticated pieces of equipment that can efficiently cut through New York's bedrock, while minimizing vibrations that could damage building foundations above. The Second Avenue subway covers a planned total length of 8.5 miles, once all phases are complete. To put the scale of this project into perspective, the total length of the new subway line would be equivalent to more than 146 football fields laid end to end. Each station is built with expansive, column-free platforms and high ceilings to enhance passenger comfort and safety, a notable departure from many of the city's older subway stations. The Second Avenue subway has faced numerous challenges, including budget overruns and delays primarily due to the complexities of constructing a new subway line in one of the world's most built-up urban environments. Comparatively, the cost and scope of the Second Avenue subway are similar to those of the Crossrail project in London, although the latter is even larger in scale.
Next up, we have to check out the Federal Way Link extension. Located in Washington State, this significant extension aims to enhance connectivity between the densely populated regions south of Seattle, spanning from the Angle Lake Station through Des Moines and into Federal Way. The project, managed by Sound Transit, began construction in 2020 and is slated for completion later into 2024. With a budget of approximately $3.1 billion, the Federal Way Link extension will add 7.8 miles of new track to the existing light rail system, promising to significantly ease traffic congestion. Designing and constructing a light rail extension through heavily urbanized areas presents a variety of challenges. One major hurdle has been the need to integrate new rail lines with existing infrastructure, requiring complex engineering solutions to bridge roads, navigate through dense urban landscapes, and minimize disruption to local communities and ecosystems. Extensive tunneling and elevated track sections are key components of the project, designed to ensure that the rail service is both efficient and minimally invasive. The Federal Way extension will include 3 new stations that are being designed with a focus on accessibility, safety, and integration with other modes of transportation, such as buses and pedestrian pathways. The workforce behind this mega project includes hundreds of engineers, construction workers, and safety inspectors. Their expertise is essential in tackling the technical demands of modern rail construction, from laying tracks that can handle high-speed trains to installing sophisticated signaling and communication systems. Upon its completion, the Federal Way Link extension is expected to serve approximately 40,000 passengers daily by 2035. Let's delve into the monumental Grand Coulee Dam project, an iconic feat of engineering located on the Columbia River in Washington State. Completed in 1942, this project was a cornerstone of the New Deal, aimed at combating the economic woes of the Great Depression while harnessing the power of the mighty Columbia River. With a final price tag of $168 million, it was one of the most expensive and ambitious infrastructure projects of its time. Construction of the Grand Coulee Dam began in 1933 and required the collective effort of over 12,000 workers at its peak. These workers faced numerous challenges, including harsh weather conditions and the logistical complexities of managing such a vast construction site. The dam stretches 523 feet across and stands 550 feet tall, making it the largest concrete structure in the United States. Its creation transformed the region, providing vital hydroelectric power and irrigation that would spur agricultural and economic development. One of the most impressive aspects of the Grand Coulee Dam is its hydroelectric power capacity. Initially, it housed 3 power plants with a total generating capacity of 280 megawatts. Over the years, expansions have increased this capacity to over 6,800 megawatts, making it one of the largest power producers in the world. The dam also created Lake Roosevelt, a reservoir that spans approximately 125 square miles. This reservoir provides irrigation to over 600,000 acres of farmland, transforming arid regions into fertile agricultural lands. The agricultural productivity of central Washington owes much to the water resources provided by the Grand Coulee Dam. However, the construction of the dam was not without its controversies and challenges. It necessitated the relocation of thousands of people and had significant environmental impacts, particularly on fish populations and the livelihoods of indigenous tribes. The project's success required innovative engineering solutions, such as the use of massive cableways to transport concrete and materials across the site and careful management of the Columbia River's flow.
The Cameron LNG project in the United States is a major liquefied natural gas export facility located in Hackberry, Louisiana. This $10 billion project involves the construction of 3 liquefaction trains, each capable of producing 4 million tons of liquefied natural gas per year. The construction includes the installation of advanced liquefied natural gas processing equipment, storage tanks, and extensive pipeline infrastructure to transport natural gas to the facility. One of the primary challenges is ensuring the safety and efficiency of the liquefaction process, which involves cooling natural gas to -260 degrees Fahrenheit. Advanced cryogenic technologies and safety systems are employed to manage the extreme temperatures and pressures involved. The project also includes the construction of a marine terminal with loading facilities to accommodate liquefied natural gas carriers. Extensive environmental assessments and mitigation measures are implemented to minimize the impact on local ecosystems and communities. Once completed, the Cameron Liquefied Natural Gas Project will significantly increase the United States' liquefied natural gas export capacity, contributing to global energy security and economic growth. The project is expected to generate substantial economic benefits, including job creation and increased investments in the local economy. The Cameron Liquefied Natural Gas Project highlights the United States' growing role as a major exporter of liquefied natural gas and its contribution to global energy markets. The construction process employs specialized machinery such as cryogenic storage tank fabrication units, high-capacity pipeline construction equipment, and advanced safety monitoring systems to ensure the safe and efficient development of the liquefied natural gas facility. Let's move over to the United States next, where the Silicon Valley Clean Water Project is located. This $500 million project involves constructing new treatment facilities and rehabilitating existing infrastructure to improve the efficiency and sustainability of the wastewater treatment process. The project includes the construction of a new wastewater treatment plant, which features advanced treatment technologies such as membrane bioreactors and ultraviolet disinfection. Membrane bioreactors are a combination of a biological treatment process and membrane filtration. They offer superior treatment performance compared to conventional methods, providing high-quality effluent by filtering out fine particles and microorganisms. Ultraviolet disinfection is another advanced technology employed in the project. UV disinfection involves exposing treated wastewater to ultraviolet light, which inactivates pathogens and microorganisms by damaging their DNA. This method is highly effective and does not involve the use of chemicals, making it an environmentally friendly alternative to traditional chlorination. The project also involves the rehabilitation of existing infrastructure, including replacing aging pipelines and upgrading pump stations. The pipelines are critical for transporting wastewater to and from the treatment plant. Engineers use trenchless technology, such as cured-in-place pipelining, to rehabilitate the pipelines without extensive excavation. This method involves inserting a resin-coated liner into the existing pipe and curing it in place, creating a new, durable pipe within the old one. Another critical component of the project is the construction of new storage and equalization tanks. These tanks are designed to manage the flow variations in the wastewater treatment process, ensuring a consistent and controlled flow of wastewater through the treatment plant. The construction of the Silicon Valley Clean Water Project also involves extensive earthworks to prepare the site for the new facilities. This includes land grading, excavation, and soil stabilization. Land grading involves reshaping the land surface to achieve the desired elevations and slopes for the treatment plant. But what about one of the tallest skyscrapers in New York City? Located in the bustling Hudson Yards district of Manhattan, the Spiral Tower stands as a pinnacle of architectural innovation and modern design. Officially known as 66 Hudson Boulevard, this towering skyscraper reached its completion in 2022, emerging as one of the most distinctive profiles against the Nick skyline due to its spiraling green terraces that ascend with the building's rise. The spiral spans 65 stories, measuring approximately 141 feet in height. The project carried a substantial financial commitment, with development costs estimated at around $3.7 billion. The construction of the spiral employed approximately 7,600 workers across various phases, reflecting its scale and the complexity of its design. This architectural marvel was conceived to offer a blend of premium office spaces and expansive green outdoor terraces on each floor, integrating nature into the urban workspace. Each terrace is equipped with foliage and seating areas, providing accessible outdoor space to office occupants, a rare feature in Manhattan's dense urban landscape. The construction of the spiral involved innovative building techniques, particularly in the integration of its steel superstructure with the cascading terraces. Advanced computer modeling and precision fabrication were crucial to ensuring that each floor's outdoor space seamlessly aligns with the spiraling design. The spiral's total floor area is about 2.8 million square feet, roughly equivalent to the size of 50 football fields. However, the project wasn't without challenges. Its construction phase coincided with the pandemic, which posed significant logistical challenges, delaying materials and reducing workforce efficiency due to health and safety protocols. Yet, the project team adapted with enhanced safety measures and scheduling adjustments to mitigate these impacts.
The Central Artery Tunnel Project, famously known as the Big Dig, in Boston, Massachusetts, stands as one of the most complex urban infrastructure projects ever undertaken in the United States. Originally estimated at $2.8 billion, the project's costs skyrocketed to over $21.9 billion by its completion. Spanning from 1988 until 2006, the Big Dig aimed to address the chronic traffic congestion on Boston's Central Artery by relocating it underground and extending the Massachusetts Turnpike through a new tunnel under Boston Harbor. A key feature of the Big Dig was the construction of the Ted Williams Tunnel, the first major component completed in 1995, which extends I-90 to Logan Airport. Did you know that the project utilized over 3.8 million cubic yards of concrete, enough to lay a sidewalk 3 feet wide from Boston to San Francisco? The Leonard P. Zachem Bunker Hill Memorial Bridge is also part of this project, being the world's widest cable-stayed bridge, celebrated for its aesthetic appeal and structural design. We have to travel to Chicago for the next megaproject. The Chicago Deep Tunnel Project, formerly known as the Tunnel and Reservoir Plan, is an ambitious civil engineering project designed to address the critical issues of urban flooding and water pollution in the city. Spanning over 100 miles of deep, large-diameter tunnels located up to 300 feet beneath the city, the Deep Tunnel Project is one of the largest and most comprehensive urban water projects in the world. With a total estimated cost projected at $3 billion, one of the primary functions of the tunnel is to capture and store stormwater runoff and sewage that would otherwise overflow into the city's rivers and Lake Michigan during heavy rain events. This system can hold up to 2.3 billion gallons of stormwater, significantly reducing the frequency and severity of water pollution incidents and urban flooding in the region. The construction of the Deep Tunnel Project has been a monumental undertaking. It required the use of massive tunnel boring machines, some of the largest in the world, which have carved out tunnels with diameters ranging from 9 to 33 feet. One of the distinguishing features of the project is the construction of 3 immense reservoirs designed to work in conjunction with the tunnels. The largest of these, the Thornton Composite Reservoir, was completed in 2015 and covers 300 acres, making it one of the largest man-made reservoirs for stormwater management in the world. Its capacity is so vast that it could theoretically hold all the water used to fill over 2,000 Olympic-sized swimming pools. In comparison to other megaprojects, such as the Boston Big Dig or the London Sewer System Upgrade, the Chicago Deep Tunnel Project stands out for its scale and its focus on water management in a densely populated urban setting.
Station expansion in the United States is a major infrastructure project designed to increase the capacity and improve the functionality of one of the busiest transportation hubs in the country. The project includes the construction of new concourses, platforms, and support infrastructure to accommodate growing passenger demand and enhance the overall experience for travelers. The construction of the new concourses involves extensive excavation, concrete pouring, and steel erection to create large, open spaces for passengers. These concourses are designed with modern amenities, including seating areas, retail spaces, and digital displays to provide information and entertainment. The construction process requires careful coordination to integrate the new concourses with the existing station infrastructure and ensure minimal disruption to ongoing operations. The new platforms are designed to accommodate longer and more frequent trains, increasing the station's capacity and efficiency. The construction of these platforms involves the installation of tracks, signaling systems, and safety features to ensure smooth and reliable train movements. The platforms are equipped with modern amenities, such as seating, lighting, and accessibility features to enhance passenger comfort and safety. In addition to the concourses and platforms, the project includes the construction of support infrastructure, such as ventilation systems, electrical networks, and emergency response facilities. These elements are essential for the safe and efficient operation of the station, providing the necessary support for passengers and staff. The construction of this infrastructure involves the installation of advanced systems and equipment to manage air quality, power supply, and safety in the station. The successful completion of the New York Penn Station expansion represents a significant investment in the future of New York's transportation infrastructure. The project enhances the capacity and functionality of the station, improving the overall experience for travelers and supporting the city's economic growth. Let's travel to Los Angeles for the LAX International Airport Modernization Project. The initiative is slated for completion in 2028 prior to the Olympic Games, and is currently one of the most significant infrastructure undertakings in the United States, with a budget exceeding $14 billion. Spanning over 1,700 acres, the airport project aims to accommodate increasing passenger numbers, projected to rise to over 100 million annually by the end of the decade. This extensive modernization includes the construction of new facilities, enhancement of existing structures, and the introduction of innovative transport systems. The project involves the addition of more than 3 million square feet of terminal space, effectively increasing the airport's size by 25%. This addition is equivalent to about 42 football fields laid side by side. The centerpiece of the project, the midfield satellite concourse, alone spans 750,000 square feet, featuring 12 new aircraft gates. Additionally, the project features a centralized utility plant upgrade that employs 6,000 solar panels and an advanced water reclamation system, which together aim to cut energy consumption by up to 25%. Challenges faced during this vast project include maintaining airport operations during construction. Solutions have involved intricate phasing of construction activities and the use of real-time analytics to manage flow and logistics across the sprawling site.
Let's move on to an even more expensive megaproject in one of the biggest cities in the country, the Las Vegas Allegiant Stadium. Home to the NFL's Las Vegas Raiders and located right next to the famous Strip, this colossal structure was developed with a staggering construction cost of approximately $1.9 billion. The funding for Allegiant Stadium is a tale of public and private partnership. Approximately $750 million came from public funds, sourced from Clark County hotel taxes, marking one of the largest public contributions to a sports facility in the United States. But what makes this stadium worth nearly $2 billion? Beyond its 65,000-seat capacity, the stadium features a retractable field and a massive translucent roof, offering fans a comfortable and visually stunning environment regardless of the desert heat. Next up, it's time to talk about the Bob Graham Sunshine Skyway Bridge project. Opened in 1987, this bridge is not just a crucial conduit connecting St. Petersburg with Terra Sia, but also a masterpiece of engineering. Spanning a total length of 4.1 miles, with a soaring cable-stayed section that stretches 1,200 feet between pylons, the Sunshine Skyway Bridge stands as one of the longest cable-stayed concrete bridges in the world. Constructed at a cost of $244 million, it was developed in response to a catastrophic collision in 1980, when the original bridge was struck by a freighter during a storm, causing a portion to collapse. This new bridge was designed to prevent such a disaster from recurring, featuring 430-foot tall pylons and a road deck that rises 193 feet above the water, allowing ample clearance for ships passing underneath, thus significantly mitigating the risk of ship collisions. The design of the Sunshine Skyway Bridge integrates advanced engineering techniques, including the use of high-strength, corrosion-resistant steel and aerodynamic concrete pylons, ensuring durability against harsh marine conditions and the threat of hurricanes. The bridge's cables, if laid end-to-end, could stretch over 300 miles, long enough to reach from Tampa to Key West. The construction process itself was a monumental task, employing over 1,000 workers at its peak. These workers braved the challenging conditions of open water to erect the massive pylons and hang the bridge's 21,000 miles of cable. The project not only demanded precision in execution, but also required innovative solutions to minimize environmental impact. It's time to explore the Crescent Dunes Solar Energy Project next, which is a groundbreaking renewable energy initiative located near Tonopah, Nevada. Completed in 2015, this state-of-the-art solar power plant represents a significant leap in solar energy technology, with a price tag of $1 billion. The Crescent Dunes Solar Energy Project was developed by SolarReserve and is renowned for its innovative use of concentrated solar power technology. Unlike traditional photovoltaic solar plants, Crescent Dunes uses a central tower surrounded by over 10,000 mirrors, known as heliostats. These mirrors track the sun and focus its energy onto the tower, heating molten salt to extremely high temperatures. One of the key advantages of this system is its ability to store thermal energy, allowing the plant to generate electricity even after the sun has set. The Crescent Dunes facility has a capacity of 110 megawatts and can provide power to approximately 75,000 homes. Building the Crescent Dunes Solar Energy Project was a massive undertaking, requiring the coordination of over 1,000 workers during peak construction phases. The project faced numerous challenges, including logistical hurdles related to transporting and assembling the large number of heliostats and constructing the central tower, which stands at 640 feet tall. The project's location in the Nevada desert posed additional difficulties, such as extreme weather conditions and the need to protect the fragile desert ecosystem. Despite these challenges, the project was completed on time and has set a new standard for solar power plants worldwide.
Let's take a look. It's time to travel to the state of Texas, where Tesla's Gigafactory is located. This sprawling facility, initiated in July 2020, underscores Tesla's commitment to scaling up its production capabilities, particularly for the Tesla Cybertruck, Model Y, Model 3, and Tesla Semi. Occupying over 2,500 acres along the Colorado River, Giga Texas is designed to be an eco-friendly facility, integrating closely with the surrounding environment. The site is one of the largest buildings in the world by footprint, featuring approximately 10 million square feet of operational space spread over several floors. This size equates to about 172 football fields, providing a visual of the vast scale of this project. The total investment by Tesla into this project is expected to exceed $1 billion, which is anticipated to inject significant economic activity into the local and state economy through direct employment and ancillary benefits to suppliers and service providers. Giga Texas is pivotal in solving the logistical challenges associated with Tesla's supply chain, aimed at reducing shipping costs and production bottlenecks. It is set to become a critical hub for Tesla's operations in the eastern United States, enhancing the company's distribution logistics across the East Coast and international markets. The factory's location was strategically chosen for its proximity to rail and road networks, facilitating efficient material shipments and distribution of finished vehicles.
But a truly stunning achievement is constructing the most expensive building in the United States. That's what Apple achieved with its Apple Park project, their futuristic headquarters located in Cupertino, California. Completed in 2017, this remarkable campus was constructed at an estimated cost of approximately $6 billion. Designed by the renowned architect Norman Foster, Apple Park is often referred to as the spaceship due to its circular, futuristic design. Spanning 175 acres, the main building covers 2.8 million square feet and accommodates over 12,000 employees. The construction of such a massive structure required one of the largest uses of curved glass for the building's exterior to achieve the seamless, minimalist aesthetic envisioned by Steve Jobs. A key focus of Apple Park's construction was its environmental impact. The campus operates on 100% renewable energy, featuring solar panels that generate 17 megawatts of power, making it one of the largest solar energy installations in the world on a corporate site. Did you know that the landscaping of Apple Park is as meticulously designed as the building itself? Over 9,000 drought-resistant trees were planted, creating a lush canopy that integrates the campus seamlessly into the surrounding environment. It's time to investigate the Interstate 70 East project next. This ambitious project, stretching 10 miles from Brighton Boulevard to Chambers Road, is designed to modernize and expand one of the busiest and most critical highway corridors in the state. Launched in 2018 and completed in 2022, the project has an estimated cost of $1.2 billion. One of the most groundbreaking aspects of the Interstate 70 East project is the reconstruction of a 1.8-mile segment of the highway that includes lowering the interstate between Brighton and Colorado Boulevards and placing a 4-acre parkland cap over a portion of the lowered interstate. This innovative design not only facilitates connectivity between the divided neighborhoods of Globeville, Elyria, and Swansea, but also adds much-needed green space to the urban environment. The project includes the widening of the interstate to accommodate one new express lane in each direction, enhancing throughput and reducing travel time. The total width of the newly designed segments reaches up to 300 feet, including new service roads and auxiliary lanes designed to improve local traffic flow alongside the interstate traffic. Construction of the Central 70 has involved massive logistical challenges, including the management of around 5,000 daily construction workers and the strategic phasing of demolition and construction to keep the interstate operational throughout the project. Next, let's examine the New Orleans Flood Protection System, a monumental infrastructure project designed to safeguard the city from devastating floods. This extensive system, with a staggering investment of $14.5 billion, stands as a critical response to the catastrophic impact of Hurricane Katrina in 2005. The system encompasses a complex network of levees, floodwalls, pump stations, and surge barriers designed to withstand a 100-year storm event. A key component of the system is the Inner Harbor Navigation Canal Surge Barrier, one of the largest civil works projects in the United States. This massive barrier stretches nearly 2 miles and features a series of gates and pumps that can be activated to block storm surges from entering the city. The INC surge barrier alone cost $1.1 billion and plays a vital role in protecting New Orleans from potential flooding. Another significant element is the Lake Borgne surge barrier, which extends for 1.8 miles and is designed to prevent storm surge from entering the Gulf Intracoastal Waterway and the Mississippi River Gulf outlet. This barrier, coupled with numerous floodwalls and levee improvements, forms a robust defense against rising waters. The construction of the flood protection system was a massive undertaking, involving tens of thousands of workers and extensive coordination between federal, state, and local agencies. The project faced numerous challenges, including the technical difficulties of working in a region characterized by soft, shifting soils and the need to protect the unique ecosystems of the Louisiana wetlands. In addition to physical barriers, the system incorporates advanced pump stations capable of removing vast amounts of water from the city's drainage canals. These pumps are essential for managing heavy rainfall and preventing water from accumulating in low-lying areas, which are particularly vulnerable to flooding.
The Royal Gorge Bridge in the United States is undergoing a major renovation project to enhance its structural integrity and improve visitor experience. Spanning 260 feet across the Arkansas River in Colorado, the bridge is one of the highest suspension bridges in the world, towering 955 feet above the river. The renovation involves replacing the wooden deck with high-strength, weather-resistant materials to ensure durability and safety. Advanced construction techniques, such as the use of prefabricated components and modular assembly, are employed to minimize disruption to visitors and ensure precision. One of the primary challenges is maintaining the structural integrity of the historic bridge while incorporating modern materials and technologies. The project also includes the installation of new safety features, such as reinforced railings and automated monitoring systems to detect structural stresses. The renovation aims to preserve the bridge's historic character while enhancing its functionality and safety. Once completed, the Royal Gorge Bridge will continue to be a major tourist attraction, providing breathtaking views and a unique engineering marvel for visitors to enjoy. The renovation also includes improvements to the surrounding infrastructure, such as upgraded walkways and viewing platforms, enhancing the overall visitor experience. The project is expected to boost the local economy by attracting more tourists and providing new job opportunities in the tourism sector. The Royal Gorge Bridge renovation underscores the importance of preserving historic structures while adapting them to meet modern safety and usability standards. The construction process utilizes specialized machinery such as high-capacity cranes, prefabrication assembly lines, and automated monitoring systems to ensure the structural integrity and longevity of the bridge. But what about the redevelopment of an entire train station? That's what happened with New York's Moynihan Train Hall. This grand project, completed in January 2021, seamlessly blends state-of-the-art facilities with historic architectural elements. The project cost approximately $1.6 billion, a strategic investment aimed at reviving the Midtown area and providing New York commuters and travelers with a more dignified and spacious environment. Construction of the train hall was a logistical challenge, requiring the coordination of thousands of workers in a densely populated urban area. The workforce fluctuated throughout the project, peaking at around 1,200 workers during its most intense phases. These individuals were involved in intricate tasks ranging from restoring the century-old steel trusses to integrating modern technology and security systems within the structure. The Moynihan Train Hall solves several pressing problems associated with the original Penn Station: overcrowding, lack of natural light, and limited amenities. By expanding into the Farley Building, the project has effectively increased the station's total footprint, allowing it to serve up to 700,000 passengers daily. The hall's design features a dramatic 92-foot-high skylight that arches over the main concourse. This skylight, covering an area of 31,000 square feet, not only illuminates the space with natural light, but also serves as a modern counterpoint to the Farley Building's Beaux Arts facade.
But we haven't even started talking about the colossal airport project the United States has worked on. Let's fly over to Denver International Airport, which was completed in 1995 and was initially budgeted at $1.7 billion, but eventually soared to nearly $5 billion, reflecting the project's scale and the complexities encountered during its development. One of the most iconic features of the airport is its striking tent-like roof structure, designed to mimic the snow-capped Rocky Mountains and pay homage to Native American teepees. The construction of Denver International was fraught with challenges, leading to delays and cost overruns. One significant factor was the airport's advanced baggage handling system, which was one of the most sophisticated and automated systems designed at the time. However, its implementation proved problematic, causing operational issues that contributed to the airport's opening being delayed by 16 months. Did you know that the airport's runway system was designed to be the most efficient and flexible of any airport globally? Its layout allows for simultaneous takeoffs and landings in almost any weather condition, reducing delays and improving safety. Next up, it's time to visit the Mackinac Bridge project. Known affectionately as Big Mac or Mighty Mac, this bridge links Michigan's upper and lower peninsulas, thus uniting what nature had divided. Located in Michigan, the Mackinac Bridge was completed in 1957 after 3.5 years of construction, overcoming numerous challenges posed by geography and climate. At the time of its completion, the Mackinac Bridge was the world's longest suspension bridge between anchorages, a title it held for many years. Spanning an impressive total length of about 5 miles, with a central span of 3,800 feet, the bridge was a marvel that required extraordinary engineering prowess and innovation. The construction cost was approximately $100 million, equivalent to nearly $1 billion today. Constructing the Mackinac Bridge was a colossal undertaking involving the coordination of hundreds of workers. The project faced many challenges, including harsh weather conditions that could change swiftly, posing risks to workers and the structural integrity of the emerging bridge. Winter gales and fog were routine obstacles that required innovative solutions, such as heated scaffolds and special gear for workers. One of the most notable aspects of the Mackinac Bridge's construction was the use of pioneering techniques for deep water caisson construction. These massive caissons were sunk to depths of up to 210 feet below the water's surface, a groundbreaking achievement at the time. The bridge's towers, standing at 552 feet above water level, required the transportation and assembly of thousands of tons of steel, sourced from mills across the United States. The Mackinac Bridge greatly simplified travel between the two peninsulas, which previously relied on a ferry service that was often hindered by ice in winter. The total amount of steel used in the bridge, approximately 20 tons, is enough to build nearly 400 tanks. Next up, let's delve into the monumental Houston Metrorail expansion project, a $7.5 billion undertaking that aims to revolutionize public transit in Houston, Texas. Spanning an impressive 20 miles of additional track, the Metrorail expansion is designed to connect more neighborhoods and increase accessibility across the city. The project involves intricate construction phases, which began in earnest in 2021 and are scheduled to reach completion by 2028. Over the course of these 7 years, the landscape of Houston will see transformative changes. Houston's flat and expansive geography presents unique challenges. Engineers are continuously combating the city's soft soil, which is prone to shifting and sinking. This has led to the innovative use of deep concrete pilings and reinforced steel to ensure the stability of tracks and stations. The project also incorporates elevated sections and raised platforms designed to withstand Houston's frequent floods, thereby safeguarding the transit system's operational integrity during severe weather conditions. Each new station along the expansion route is being built with more than functionality in mind. They are envisioned as community hubs, equipped with modern amenities, real-time travel information, and artwork reflective of local culture. Despite the benefits, the path hasn't been entirely smooth. Issues ranging from logistical challenges, such as coordinating with existing traffic and utility lines, to public opposition concerning construction disruptions, have tested the project's resilience. The project management team has had to innovate on the fly, employing cutting-edge construction techniques and real-time problem-solving to keep the project on track. Specialized construction methods, like the use of silent piling technology to minimize noise in residential areas, and the application of advanced GPS and GIS for precision in layout and execution, highlight the technical sophistication of this expansion. Let's move over to the United States for the New River Gorge Bridge. Spanning 3,030 feet across the New River Gorge, this arch bridge boasts a main span of 700 feet, making it one of the longest single-span arch bridges in the world. The bridge sits 876 feet above the New River, offering breathtaking views and dramatically improving transportation in the region. The construction of the New River Gorge Bridge was a monumental task, requiring innovative solutions to the challenges posed by the gorge's rugged terrain and the river below. The design utilizes a steel arch, chosen for its strength and ability to span long distances without the need for support piers in the river, which would have been difficult to construct and maintain. One of the most impressive aspects of the construction process was the method used to assemble the arch. Prefabricated sections were lifted into place using cables strung across the gorge. This method required precise engineering and coordination to ensure each section was correctly aligned and secured. The steel used in the bridge's construction was specially treated to withstand the area's environmental conditions, ensuring its durability and longevity. The bridge's deck, supported by the arch below, carries 4 lanes of traffic and has significantly reduced travel time between the region's communities. Before the bridge's construction, travelers had to navigate a treacherous 40-minute journey down narrow, winding roads to cross the gorge. The New River Gorge Bridge has cut this travel time to less than a minute, fostering economic development and improving access to the area's natural beauty.
It's time to travel over to the United States for the Gilmerton Bridge Replacement Megaproject. The new bridge, costing approximately $134 million, aims to improve traffic flow and safety for the thousands of vehicles and vessels that pass through this vital corridor daily. Construction of the Gilmerton Bridge replacement began in 2009, with the new bridge opening to traffic in 2013. The new bridge is a vertical lift bridge, which provides several advantages over the old bascule bridge. The vertical lift design allows for a higher clearance for maritime traffic, reducing the number of bridge openings and minimizing delays for both road and river traffic. The new bridge features a vertical clearance of 35 feet when closed and up to 135 feet when fully lifted, accommodating larger vessels that navigate the river. The construction of the bridge involved several advanced engineering techniques. The bridge's foundations were constructed using drilled shafts, which provide greater stability and load-bearing capacity compared to traditional pile foundations. These shafts were drilled deep into the riverbed, ensuring the bridge could support the heavy traffic loads and withstand the harsh environmental conditions of the river. One of the key innovations in the Gilmerton Bridge Replacement Project was the use of precast concrete segments for the bridge's superstructure. These segments were manufactured off-site and transported to the construction site, where they were assembled using a balanced cantilever method. The project also included significant upgrades to the bridge's mechanical and electrical systems. The new bridge is equipped with state-of-the-art lifting machinery and control systems, ensuring reliable and efficient operation. The project included the construction of new pedestrian and bicycle pathways, enhancing accessibility and promoting alternative modes of transportation. It's time to move over to Boston now for the Green Line Extension Megaproject. This extension aims to enhance public transit services by connecting the densely populated but underserved areas of Somerville and Medford to the existing subway network, thereby increasing accessibility to central Boston. Launched with major construction efforts ramping up around 2018, the GLX project completed in 2023. The project's budget, initially estimated at $2 billion, saw an increase to nearly $3 billion due to unforeseen construction and environmental challenges. Spanning approximately 4.7 miles, the GLX adds 7 new stations along 2 branches, one terminating at Union Square in Somerville and the other at Tufts University in Medford. These new tracks and stations are expected to serve about 45,000 riders daily, significantly easing traffic congestion and reducing commute times in these high-density corridors. The workforce required for this mammoth project varied throughout its phases, involving up to 1,000 construction workers and engineers at peak times. One of the most critical problems the GLX project addresses is the reduction of vehicle emissions by providing a reliable and efficient public transit alternative, thereby contributing to the state's environmental goals. In terms of construction, the GLX employed advanced methods, including the use of track-laying machines that allowed for faster, more efficient installation of rail lines. This project also involved substantial upgrades to existing infrastructure, such as the improvement of bridges and roads along the extension path, ensuring that the new service would be integrated smoothly with minimal disruption. Challenges encountered during the GLX project included managing complex logistics in densely populated areas, mitigating noise and disruption to local communities, and addressing cost overruns and delays, which were exacerbated by the pandemic.
But now it's time to talk about the longest and most expensive pipeline megaproject ever constructed in the country. The Trans-Alaska Pipeline System, stretching approximately 800 miles, represents one of the most significant achievements in pipeline construction. Completed in 1977 at a cost of $40 billion, the project was constructed to transport oil from North America's largest oil field in Prudhoe Bay to the ice-free port of Valdez. One of the most notable is its earthquake-proof design, featuring sliding supports that allow the pipeline to move during seismic activity without rupturing. Approximately half of the pipeline is elevated on more than 78,000 vertical support members to prevent the thawing of permafrost, which could destabilize the structure. This design allows cold air to circulate around the pipes, helping to maintain the permafrost's integrity. Did you know that the pipeline system includes the crossing of over 800 rivers and streams? The project's scale necessitated the largest private air force at the time to transport workers and materials, highlighting the logistical challenges overcome during construction. The pipeline can transport up to 2.1 million barrels of oil per day, showcasing its critical role in the U.S. energy infrastructure. But how about a massive interstate megaproject? In the heart of Texas, the North Tarrant Express project stands as a testament to transformative infrastructure innovation. Initiated in 2010 and completed in 2014, this project revolutionized 13.3 miles of Northeast Loop 820, an airport freeway designed to address the burgeoning needs of one of the fastest-growing regions in the United States. The project, costing approximately $2.1 billion, wasn't just about expansion. It was about reimagining mobility. By incorporating managed toll lanes known as Texpress lanes, the North Tarrant Express introduced dynamic pricing to manage traffic flow, a first of its kind in Texas. These lanes adjust prices based on real-time traffic conditions, optimizing roadway usage and drastically reducing congestion. Traditional road expansions of this magnitude typically span decades, yet this project compressed timelines into a mere 4 years of construction, all while keeping the highway open. This feat was achieved through around-the-clock work and an innovative approach to staging and materials handling that minimized disruptions to the daily lives of nearly 200,000 drivers. This immense undertaking required the coordination of thousands of workers, from engineers who redesigned interchanges to support smoother traffic flow to expansive construction teams. The North Tarrant Express implemented several green initiatives, such as using recycled materials for roadbeds and deploying advanced stormwater management systems to protect the region's waterways, setting a new standard for eco-friendly construction practices in large-scale infrastructure projects. Moreover, the economic impact of the North Tarrant Express has been profound. By improving access and reducing travel times, the project has spurred growth in local communities, enhanced property values, and attracted new businesses looking to capitalize on improved logistics and accessibility. It's time to delve into the American Dream Meadowlands, a massive entertainment and retail complex located in East Rutherford, New Jersey. With a staggering cost of $5 billion, this ambitious project represents one of the largest mall developments in the United States. Officially opened in phases starting in 2019, American Dream Meadowlands covers approximately 3 million square feet. One of the most striking features of American Dream is its Nickelodeon Universe theme park, the largest indoor theme park in the Western Hemisphere. Adjacent to this is the DreamWorks Water Park, which boasts the largest indoor wave pool. The project faced numerous challenges during its development, including financial difficulties and multiple changes in ownership. Originally conceived in early 2000, the development stalled several times due to economic downturns and funding issues. Despite these setbacks, the project was revitalized and eventually brought to completion, marking a significant milestone in the region's commercial landscape. American Dream's indoor ski slope, known as Big Snow, is another highlight of the complex. It is the first indoor real snow ski and snowboard park in North America, offering year-round winter sports activities. This unique attraction allows visitors to enjoy skiing and snowboarding regardless of the season, making it a significant draw for tourists and locals alike. The construction of American Dream Meadowlands required the coordination of thousands of workers and involved complex engineering and architectural solutions to create its diverse range of attractions. The developers also focused on sustainability, incorporating energy-efficient systems and environmentally friendly practices throughout the complex. The project's strategic location near New York City and major transportation hubs enhances its accessibility, attracting visitors from across the region and beyond. Let's travel to the state of Virginia for a bridge project that moves the price bar even higher. The Woodrow Wilson Bridge project connecting Alexandria, Virginia, with Oxon Hill, Maryland, over the Potomac River, was reimagined to address the burgeoning traffic demands of the Washington, D.C. metropolitan area. The project's total cost, exceeding $3.4 billion, highlights its scope and the complexity of its execution. The decision to make the project a drawbridge, the world's second largest of its kind, was driven by the necessity to accommodate large ship traffic along the Potomac River. Did you know that the bridge's construction included a wide array of environmental considerations? For instance, measures were implemented to protect the Potomac River's water quality and to relocate affected wildlife.
But how about an entire stadium being replaced? The Aloha Stadium Replacement Project, located in Halawa, Hawaii, is a significant undertaking aimed at revitalizing the sports and entertainment capabilities of Hawaii's most populous island, Oahu. This ambitious project replaces the aging Aloha Stadium, originally built in 1975, which had become increasingly costly to maintain and no longer met modern safety or functionality standards. Scheduled for completion in 2028, the new stadium complex is anticipated to cost over $350 million. The project covers an extensive area of approximately 98 acres, with the new stadium expected to seat around 35,000 spectators, down from the old stadium's capacity, but designed to offer improved sightlines and amenities. This size makes it comparable to the StubHub Center in California, though with enhanced technological integrations. Employing around 2,000 workers during peak construction phases, The project faces the unique challenges of building in an island setting, such as logistics complications related to material shipping and the high cost of labor and supplies in Hawaii. The new stadium will employ modern construction techniques, including the use of sustainable materials and energy-efficient designs to minimize its environmental footprint. Features like solar power generation and water reclamation systems are planned to make it one of the greenest stadiums in the nation. A key problem that the new Aloha Stadium aims to solve is the economic inefficiency of its predecessor. The old stadium was underutilized, partially due to its deteriorating condition and lack of modern facilities that limited event hosting capabilities. The new complex, with its state-of-the-art features, seeks to attract more high-profile events and, consequently, generate significant economic benefits for the region. One innovative aspect of the project is its integrated approach to development. The stadium complex will include mixed-use developments such as hotels, retail spaces, and residential areas, creating a vibrant community hub rather than just a sports venue. This model follows the trend seen in projects like the Atlanta Braves' Truist Park, which integrates a stadium with a larger commercial and residential district.
Located in Louisiana, the Lake Pontchartrain Causeway stands as a monumental testament to bridge engineering. Stretching a staggering 24 miles across Lake Pontchartrain, this bridge holds the title of the longest continuous bridge over water in the world. The construction of the causeway began in 1955 and was completed in 1956, with a parallel span added in 1969 to accommodate the growing traffic. The project required the installation of over 9,000 concrete pilings, each driven deep into the lakebed to ensure stability and resilience against the water's varying conditions. This engineering marvel connects the cities of Metairie and Manville, significantly enhancing regional connectivity and economic integration. The causeway's design and construction addressed numerous challenges, including the lake's depth and the need for a structure that could withstand the harsh environmental conditions. The bridge's sheer length necessitated the use of innovative construction techniques and materials to ensure its longevity and safety. It features a series of low-rise spans supported by concrete pilings, creating a durable and stable roadway that has stood the test of time. The Lake Pontchartrain Causeway not only facilitates the daily commutes of thousands of residents, but also plays a crucial role in emergency evacuations during hurricanes, highlighting its strategic importance. In terms of economic impact, the causeway has significantly boosted local businesses by improving access to the greater New Orleans area. It has also become a vital route for freight transport, supporting the movement of goods across the region. The bridge's maintenance and operational management continue to be a priority, with regular inspections and upgrades to ensure its structural integrity. Next up, it's time to investigate the Huey P. Long Bridge. Since its original completion in 1935, this bridge has stood as a vital link for both rail and vehicle traffic between the eastern and western halves of the metropolitan New Orleans area. The bridge underwent a massive expansion and renovation project that began in 2006 and concluded in 2013, drastically enhancing its capacity and safety. The project's scale was monumental, with a budget of $1.2 billion, making it one of the largest public works projects in Louisiana's history. This extensive modernization aimed to address the bridge's notorious narrow lanes, which were often seen as a bottleneck for traffic and a hazard for drivers. Originally constructed during the Great Depression as part of a nationwide infrastructure initiative, the Huey P. Long Bridge was named after the famed Louisiana Governor Huey P. Long, who was a major proponent of infrastructure projects. At the time of its initial completion, it was among the longest railroad bridges in the United States, featuring a continuous truss design that was a marvel of that era's engineering capabilities. The renovation project expanded the bridge's width, adding wider traffic lanes that increased the overall width from 18 feet to an impressive 43 feet. This expansion included the installation of new roadways and rail lines, significantly increasing the bridge's traffic capacity and safety. The bridge's elevation was a significant challenge, situated 135 feet above the Mississippi River, which necessitated complex vertical construction techniques. Engineers employed high-strength, lightweight concrete and advanced steel composites to handle the loads and stresses involved with such height and width, ensuring long-term durability against the river's powerful currents and the region's frequent severe weather. The construction work involved around 300,000 cubic yards of concrete, enough to fill 90 Olympic-sized swimming pools. But have you ever heard of the Intel semiconductor plant? With an estimated cost of $20 billion, this state-of-the-art facility represents one of the largest and most ambitious semiconductor manufacturing endeavors in the United States. Located in Chandler, Arizona, the project began its construction in 2011 and has seen continuous upgrades to remain at the cutting edge of semiconductor technology. The plant spans several 100,000 square feet and is designed to produce Intel's most advanced chips, including those built on the company's latest process technologies. A standout feature of the Intel semiconductor plant is its use of advanced manufacturing techniques, which enable the production of chips with transistors measuring just a few nanometers in size. This precision is essential for creating the powerful and efficient processors that drive today's electronics, from computers and smartphones to data centers and AI applications. The facility is also a model of sustainability and environmental stewardship. Intel has implemented numerous green initiatives at the plant, including energy-efficient designs, extensive water recycling systems, and waste reduction programs. Intel's plant plays a critical role in the company's global supply chain, helping to meet the ever-growing demand for semiconductors. This demand has been driven by the proliferation of digital devices, the expansion of cloud computing, and the increasing integration of artificial intelligence into various sectors. The plant's production capacity is essential for ensuring that Intel can supply the chips needed to power the technological innovations of today and tomorrow. The strategic importance of the Intel semiconductor plant extends beyond its manufacturing capabilities. It represents a significant investment in the U.S. economy, creating thousands of high-tech jobs and fostering innovation in the semiconductor industry. The plant also contributes to the nation's technological independence, reducing reliance on overseas chip manufacturing and enhancing the resilience of the supply chain.
It's time to travel to San Francisco next, where the gigantic Chase Center is one of the city's biggest megaprojects. Located in the Mission Bay neighborhood of the city, Chase Center serves as a state-of-the-art arena primarily for the Golden State Warriors and a versatile venue for concerts and other events. This mega project, completed in September 2019, was a private sector initiative spearheaded by the Warriors' ownership, costing an estimated $1.4 billion. Chase Center covers an area of 11 acres and includes an 18,000-seat arena, 2 office buildings, 100,000 square feet of retail space, and a public plaza. The project also involved the creation of a waterfront park along with a half-mile of restored public waterfront. One of the challenges in its development was integrating the center with San Francisco's existing public transport networks. This led to significant improvements in local infrastructure, including the addition of a Muni Metro light rail platform and the enhancement of nearby roads. The use of cutting-edge seismic technology was a focal point, considering San Francisco's susceptibility to earthquakes. This included innovative base isolators and shock absorbers that ensure the arena can withstand significant seismic events. Chase Center's unique architectural design and construction methods included the use of sweeping glass facades and intricate metalwork that complements the bay's maritime setting. If you consider the height of the arena at nearly 135 feet, it stands tall enough to house the Statue of Liberty inside it, giving a sense of the scale at which this construction was conceptualized and executed.
But what about the most costly real estate development project in the United States? The Hudson Yards redevelopment project in New York City is a beacon of urban transformation, with an estimated total cost of over $25 billion. This colossal project has reshaped the west side of Manhattan, introducing a blend of high-rise residential buildings, office towers, and restaurants. One of the project's most innovative engineering feats is the platform built over the West Side Yard, a working train yard serving the Long Island Railroad. Constructed at a cost of approximately $1 billion, this platform covers 30 tracks, 3 rail tunnels, and 2 subway lines, all of which remain operational during construction. Another highlight is the vessel, a 16-story, honeycomb-like structure of interconnected staircases. Did you know the project includes a state-of-the-art waste management system designed to eliminate the need for traditional garbage trucks? This system, an investment in sustainability and efficiency, transports waste through a series of underground tubes to a central collection point. The development also prioritizes green spaces, with more than half of Hudson Yards dedicated to public plazas and gardens. But we have to talk about a gigantic station megaproject next. Miami Central Station, strategically situated in the heart of downtown Miami, Florida, is a transformative infrastructure and transit development that epitomizes the future of urban transportation in the southeastern United States. Officially opened in 2018, this expansive multimodal hub integrates commuter rail, intercity rail, and future high-speed rail, forging a new standard for transit connectivity in the region. The project, which is part of the broader Miami Intermodal Center, required an investment of over $2 billion and brought together a wide array of transportation systems under one roof. Miami Central not only serves as a vital junction point for Brightline services connecting Miami with Fort Lauderdale and West Palm Beach, but also accommodates Metrorail and Tri-Rail services, facilitating seamless travel across multiple transit lines. Spanning several city blocks, Miami Central Station is designed with a sleek, modern aesthetic that incorporates state-of-the-art architectural elements. One of the most significant challenges during the construction was integrating the new facilities with existing transit services while minimizing disruption to daily commuters. This involved careful planning and phased construction strategies, including the strategic placement of platforms and the careful coordination of numerous construction teams working in a densely urbanized area. The station's architectural design required innovative construction techniques to support its complex, multi-level structure. This includes the use of high-strength steel and reinforced concrete capable of supporting heavy rail components and high passenger footfalls, while also withstanding Florida's challenging weather conditions, including the threat of hurricanes. In terms of scale, Miami Central's construction involved moving thousands of tons of earth and laying miles of new track activities comparable to erecting a small city. Let's delve into the Northgate Link extension, a transformative addition to Seattle's public transportation network. Completed at a cost of $1.9 billion, this project is a cornerstone of the region's efforts to enhance urban mobility and reduce traffic congestion. Breaking ground in 2012 and opening to the public in October 2021, the Northgate Link extension stretches the city's light rail system by 4.3 miles, connecting the University of Washington to Northgate. This crucial extension includes 3 new stations, strategically located to serve key residential and commercial hubs in northern Seattle. A defining feature of the Northgate Link extension is the engineering marvel of its twin tunnels, constructed using state-of-the-art tunnel boring machines. These machines, dubbed Brenda and Pamela, excavated deep beneath the city, navigating complex soil conditions and existing underground infrastructure with remarkable precision. The construction process engaged thousands of workers and required intricate planning and coordination. Each new station is designed with a focus on accessibility, safety, and community integration, featuring modern amenities and public art installations that enhance the commuter experience. The Northgate Link extension significantly reduces travel times, with the journey from Northgate to downtown Seattle now taking just 14 minutes. This improvement is expected to ease road traffic and provide a reliable alternative to driving, fostering greater use of public transportation. The project's impact on Seattle's urban landscape is profound, revitalizing neighborhoods and stimulating economic growth around the new stations.
But what about a massive dam megaproject? For that, we have to travel to the Ohio River, where the Olmsted Locks and Dam project is located. This monumental undertaking, designed to replace aging infrastructure and modernize the waterway system, is crucial for the transportation of billions of dollars worth of goods annually across central U.S. states. This project, which officially completed in 2018 after over 30 years of planning and construction, spans across the river and involved an extraordinary financial investment of approximately $3 billion. The construction required the sustained effort of hundreds of engineers, technicians, and laborers over several decades, underscoring the project's scale and complexity. The Olmsted project replaced 2 older and less efficient facilities, locks and dams 52 and 53, which had become increasingly unreliable, causing significant delays in river traffic and logistical inefficiencies. The new structure consists of a navigational pass and 2 parallel 110-foot by 182-foot locks. This setup significantly eases the river traffic, allowing for the smooth passage of approximately 90 million tons of cargo yearly. One of the notable challenges of the Olmsted Locks and Dam was its innovative construction method, specifically the use of in-the-wet technology. Unlike traditional dry dock methods, this technique involves assembling large modular sections of the dam on land, then floating them to their installation site on the river. The total amount of concrete used in the dam's construction would be enough to pave a sidewalk stretching from New York to San Francisco. A special feature of the Olmsted Locks and Dam is its resilience to seismic activity. The region is near the New Madrid fault line, and as such, the structure was designed to withstand significant earthquakes, ensuring the long-term stability and safety of this critical infrastructure. The project's importance extends beyond just its immediate functionality. By improving the reliability and efficiency of the Ohio River as a navigational channel, the Olmsted Locks and Dam also bolsters the economic viability of river transportation, which is significantly more fuel efficient and environmentally friendly compared to road and rail transport.
It's time to fly back to New York for the most expensive subway megaproject in the country. The East Side Access Project exemplifies the challenges and triumphs of urban tunneling and railway construction. With an estimated cost of over $11 billion, it ranks as one of the most expensive railway projects in the world. This ambitious project aims to connect the Long Island Railroad to a new terminal beneath Grand Central Terminal, offering a direct route that was previously unavailable to thousands of commuters. The East Side Access includes approximately 8 miles of tunneling beneath Manhattan's densely packed urban environment. These tunnels were not merely dug, but meticulously carved through some of the most challenging geological conditions, including hard rock and water-bearing sediments. Did you know that the project necessitated the excavation of about 2 million cubic yards of rock? This is equivalent to filling the Empire State Building nearly 2 times. The construction also involves the creation of a new terminal beneath Grand Central, consisting of multiple levels of concourses and platforms. This terminal is being constructed more than 140 feet below street level, requiring innovative solutions for ventilation, lighting, and passenger flow. We travel over to San Francisco next for the redevelopment of their international airport. This expansive project, known as the Airport Development Plan, is set to reshape the airport by enhancing capacity and passenger experience through a series of ambitious construction initiatives. Commenced in 2016 with a strategic plan, the development is budgeted at over $7 billion. One of the cornerstone projects within this expansion is the renovation of Terminal 1, a project that began in 2016 with a budget of approximately $2.4 billion. The terminal's revamp includes the construction of a new boarding area with additional gates, upgraded baggage systems, and new dining and retail spaces. The airport's plans also include the enhancement of airfield safety. These changes are designed to improve the efficiency of aircraft movements on the ground, thereby reducing taxi times and minimizing delays. San Francisco International Airport is also focusing heavily on sustainability, aiming to become one of the world's first zero-net energy airport campuses. Solar panels, energy-efficient buildings, and water conservation systems are integral to this vision. The challenges of executing such a vast project in an active airport environment are immense. Construction teams have had to carefully phase their work to minimize disruption to travelers, manage noise levels, and ensure that airport security is uncompromised. It's time to discuss the next megaproject. Welcome to the Treasure Island redevelopment in San Francisco. Set on a man-made island in the heart of San Francisco Bay, this project is transforming a former naval base into a vibrant residential and commercial hub. Treasure Island spans approximately 405 acres. To put that into perspective, it's roughly the size of 300 football fields laid side by side. The project's budget is a whopping $6 billion, earmarked for creating over 8,000 homes, of which a quarter are designated as affordable housing. The plan includes schools, hotels, and over 300 acres of parks, which means green space is central to the island's new identity. Construction began in 2011 and is set to continue in phases through 2035. The scale of manpower and machinery on this site is staggering. At its peak, the project employed thousands of workers, each skilled in various aspects of construction, from engineers and architects to builders and landscapers, all converging to bring this vision to life. One of the most intriguing aspects of the Treasure Island redevelopment is its commitment to sustainability. The island is poised to become one of the most eco-friendly developments in the U.S., with advanced stormwater systems, zero-waste goals, and buildings designed to lead gold standards. But it hasn't been all smooth sailing. The project has faced its share of challenges, from concerns over rising sea levels to remediation of the soil, which was contaminated during its days as a naval base. These issues required innovative solutions such as elevated land to combat potential flooding and extensive cleanup efforts to ensure the safety and sustainability of the new community. The amount of soil moved and treated for the redevelopment could fill over 60 Olympic-sized swimming pools. And if we talk about the infrastructure, the main roadway spanning the island's length is akin to laying down nearly 3 Golden Gate bridges end to end.
Let's travel over to North Carolina, where the Charlotte Gateway Station is being constructed. This significant development, a central hub designed to integrate various modes of transportation, including Amtrak, buses, and future light rail services, is part of a larger vision to improve transit connectivity across the region. Scheduled for full operational status by 2025, the Charlotte Gateway Station began its early phases in 2018 with a budget projected to exceed $800 million by the project's conclusion. The station itself will cover several city blocks, featuring a state-of-the-art passenger terminal, bus bays, and extensive parking facilities. The project's total area is comparable to 20 football fields, emphasizing its scale and the transformational impact on the city landscape. It is expected to serve thousands of passengers daily, significantly easing the city's traffic congestion and providing a more efficient, reliable public transportation network. One of the primary challenges has been coordinating the multiple phases of construction while minimizing disruptions to the existing traffic and businesses in downtown Charlotte. The station's design features include expansive glass facades to maximize natural lighting and open public spaces that encourage pedestrian traffic, reflecting new trends in urban station aesthetics and functionality. In comparison to other transportation projects like the Moynihan Train Hall in New York City, the Charlotte Gateway Station is unique in its incorporation of green building practices and its role in catalyzing economic development in a mid-sized American city. Despite challenges such as budget adjustments and the complex logistics of constructing in a dense urban core, the Charlotte Gateway Station is set to become a critical node in North Carolina's transportation network.
The next project on our list is the most expensive dam located in the United States. The Hoover Dam represents one of the most significant engineering achievements of the 20th century. With a total construction cost of over $2.7 billion, the dam's financial figures are as staggering as its physical dimensions. To construct the Hoover Dam, an estimated 5 million barrels of cement and 45 million pounds of reinforced steel were required. This was at a time when the procurement and transportation of such massive quantities of materials were incredibly challenging, contributing significantly to the overall cost. Moreover, the dam's construction provided employment for thousands of workers, offering a much-needed economic boost during a time of widespread unemployment. Did you know that the Hoover Dam also required the construction of Boulder City, a town built specifically to house the project's workers and their families? This added another layer of expense, but was essential for providing a stable and healthy living environment for the workforce. But what about the construction of a massive train station? Denver Union Station was reopened in 2014 after a comprehensive $540 million redevelopment, and the historic train station has been reimagined into a vibrant, multimodal hub that anchors Denver's thriving transit-oriented development. Originally constructed in 1881, Denver Union Station had fallen into disrepair and underutilization by the late 20th century. The bold revitalization project, which began in earnest in 2010, was spearheaded by a public-private partnership aiming to revitalize the area while preserving its historic charm. The project covered 19.5 acres and involved the integration of light rail, Amtrak, buses, and new pedestrian and bicycle pathways, creating a nexus of connectivity for the city and the region. One of the most compelling aspects of the Union Station project was the creation of an underground bus concourse. This 22-gate facility spans nearly 1,000 feet in length roughly, the length of 3 football fields situated beneath 1.5 acres of public plaza that includes fountains and space for public events. This innovative design successfully separates bus traffic from pedestrian areas, enhancing safety and urban aesthetic. The station itself houses more than 110,000 square feet of mixed-use development, including retail shops, restaurants, and a hotel, which occupy the historic terminal building. The Denver Union Station project's challenge was to integrate seamlessly into the existing urban fabric, preserving historical elements like the station's iconic travel by train neon sign while introducing cutting-edge infrastructure. Moreover, the project team faced the complex task of coordinating multiple transportation systems in a tight urban core, all while maintaining service for thousands of daily commuters. The economic impact has been profound, with billions of dollars in private investment flowing into the surrounding area since the station's reopening. Next, let's explore the Las Vegas Convention Center expansion. With a total investment of $4.3 billion, this expansion project significantly enhances the capabilities and allure of one of the world's largest convention centers. Officially completed in 2021, the Las Vegas Convention Center expansion spans 1.4 million square feet, adding substantial new space to the existing facility. The project includes the new West Hall, which alone provides an additional 600,000 square feet of exhibit space, complemented by a stunning 14,000 square foot outdoor terrace offering breathtaking views of the Las Vegas Strip. One of the most innovative aspects of the expansion is the integration of the LVCC Loop, an underground transportation system developed by Elon Musk's The Boring Company. This system features autonomous electric vehicles that transport attendees between the convention center's different halls at high speeds, significantly reducing transit times across the vast complex. The expansion was driven by the growing demand for large-scale event spaces in Las Vegas, which hosts numerous high-profile conventions, trade shows, and corporate events annually. Construction of the expansion required the coordination of thousands of workers and the use of cutting-edge building techniques to ensure that the project met its ambitious goals on time and within budget. Despite the challenges posed by the pandemic, the project team implemented rigorous health and safety protocols to keep the work on track. Sustainability was also a key focus of the expansion, with the new West Hall designed to achieve LEED certification for its environmentally friendly features. These include energy-efficient lighting, water-saving fixtures, and the use of sustainable materials throughout the construction process. In addition to the increased exhibit space, the expansion features advanced technological infrastructure, including high-speed internet and state-of-the-art audiovisual capabilities to meet the needs of modern events and exhibitions.
Next up, we have to talk about the Atlanta Beltline project. Envisioned as a comprehensive revitalization effort, the Beltline aims to convert a historic 22-mile railroad corridor encircling downtown Atlanta into a multi-use trail, modern streetcar line, and expansive green space. This grand project, which began in the early 2000s and is expected to continue in phases through 2030, is not only redefining urban transit, but also enhancing community connectivity. With an estimated cost exceeding $4.8 billion, the Atlanta Beltline is one of the largest, most wide-ranging urban redevelopment projects in the United States. It involves the coordination of multiple city departments and private contractors, engaging thousands of workers over its multiple phases of development. The Beltline addresses several critical urban challenges, including the need for improved public transportation options. By connecting 45 in-town neighborhoods with multi-use trails and transit options, it promotes a more sustainable lifestyle, reducing reliance on automobiles and encouraging walking, biking, and public transit. A notable feature of the Atlanta Beltline is its use of existing railroad tracks for the trail and transit system. The incorporation of art installations and parks along the Beltline has also turned previously neglected spaces into vibrant public areas that foster community interaction and cultural expression. The project has faced challenges, particularly in terms of funding and community engagement. Balancing the diverse needs and expectations of various stakeholders, residents, and city officials has required continuous dialogue and adaptation.
But an even more expensive megaproject is the Verrazano Narrows Bridge, an engineering marvel that connects the boroughs of Staten Island and Brooklyn in New York City. At the time of its completion in 1964, this bridge was the longest suspension bridge in the world. This colossal structure not only redefined the New York skyline, but also represented a significant financial undertaking, with a construction cost of approximately $3 billion. The bridge's construction necessitated not only a substantial upfront investment, but also a long-term financial strategy to ensure its sustainability. The initial toll was set to facilitate the repayment of the construction bonds, reflecting the economic principles that underpin the bridge's development. The bridge required thousands of workers and vast amounts of materials, including steel for the 42 to 60-foot-long main span, which contributes significantly to the overall expense. It's time to move over to the Blue Plains Tunnel next. This massive infrastructure project is a critical component of DC Water's Clean Rivers project, aimed at drastically reducing combined sewer overflows into the Anacostia, Potomac Rivers, and Rock Creek. The tunnel, completed in 2015, stretches over 2,400 feet in length and is located up to 160 feet below the city's surface. This tunnel was designed to capture and store sewage and stormwater runoff during heavy rains, redirecting up to 100 million gallons of overflow that would have otherwise spilled into local waterways. The project's total cost was approximately $580 million, making it not only one of the largest environmental projects in the city's history, but also a significant investment in sustainable infrastructure. Constructing such a vast underground structure in an urban environment presented numerous challenges. The project team had to navigate around existing utilities and subway tunnels, requiring precise mapping and innovative tunneling techniques. The tunnel was constructed using a tunnel boring machine named Lady Bird, a massive piece of machinery that excavated the tunnel's path while simultaneously laying reinforced concrete to form the tunnel walls. The scope of the Blue Plains Tunnel can be compared to the length of nearly 80 football fields laid end-to-end. The concrete used in the project would be enough to pave a 2-lane road for several miles. Special features of the Blue Plains Tunnel include its state-of-the-art odor control systems designed to treat air before it is vented to the surface, ensuring that the surrounding neighborhoods are not affected by unpleasant smells. It's time to explore the Kennedy Space Center, a monumental project that stands as a pinnacle of aerospace engineering. Located on Merritt Island, Florida, this iconic facility was established in 1962 and became operational during the height of the space race. The total cost of constructing and developing the Kennedy Space Center is estimated at approximately $2 billion. The Space Center spans 144,000 acres and serves as NASA's primary launch center for human spaceflight. Its construction required the efforts of thousands of engineers, technicians, and laborers working around the clock to bring this ambitious project to fruition. The center's most famous feature is Launch Complex 39, which includes 2 launch pads and the massive Vehicle Assembly Building. The VAB is one of the largest buildings in the world by volume and was designed to assemble the Saturn V rocket, the behemoth that carried astronauts to the moon during the Apollo program. The Kennedy Space Center was not just built for the Apollo missions. It has been instrumental in numerous space endeavors, including the Space Shuttle program and, more recently, SpaceX's commercial crew missions. The facility's infrastructure includes a network of crawler transporters that move rockets from the VAB to the launch pads, a distance of about 3 miles. These crawlers are engineering marvels in their own right, capable of carrying the immense weight of fully assembled rockets. One of the significant challenges faced during the construction of the Kennedy Space Center was managing the environmental impact on the surrounding Merritt Island National Wildlife Refuge. This required careful planning and innovative solutions to ensure that the center's operations did not adversely affect the local ecosystem. To understand the scale of the Kennedy Space Center, consider that its launch pads and support facilities occupy an area equivalent to about 219 football fields. The center has continuously evolved, incorporating cutting-edge technology and infrastructure to support the ever-advancing field of space exploration. The California High-Speed Rail Project is an epic venture into modernizing transportation with an initial estimate of around $33 billion that has since soared past $100 billion. Designed to connect the state's major urban centers, such as San Francisco and Los Angeles, with speeds capable of reaching 220 miles per hour, the project aims to slash travel times to under 3 hours across approximately 800 miles of track. Projected to be the first of its kind in the country, the high-speed rail's completion date has been a moving target, currently anticipated for 2033. This timeline reflects the project's vast scope and the intricate engineering challenges it faces, including the construction of over 36 miles of tunnels through the Tehachapi and San Gabriel Mountains. An exemplar of sustainable transportation, The rail project is committed to operating on 100% renewable energy, with stringent environmental protections integrated into its development to minimize impacts on natural habitats. Despite facing financial scrutiny and logistical obstacles, such as securing adequate funding and navigating the complexities of state and federal regulations, the California high-speed rail continues to push forward. But what about the expansion of a massive airport? The O'Hare International Airport expansion is one of the most ambitious airport revitalization efforts in the world. Located in Chicago, Illinois, this massive undertaking aims to propel O'Hare into the future of aviation. With a projected budget of $8.5 billion, this expansion is not just a facelift, but a complete transformation aimed at increasing capacity and improving efficiency. Officially launched in 2019, the O'Hare 21 project is slated for completion in 2028. It includes a major overhaul of Terminal 5, the construction of a new Global Terminal 2, and the addition of 2 new satellite concourses. These improvements will expand terminal space by a staggering 60%, allowing O'Hare to handle the anticipated increase in passenger traffic, which is expected to exceed 100 million passengers annually by the project's completion. The centerpiece of the expansion is the new Global Terminal, designed to be the first of its kind in the United States, which will replace the existing Terminal 2. The terminal will cover approximately 2.2 million square feet, making it one of the largest aviation facilities in the country, roughly equivalent in size to 35 football fields. Construction at one of the busiest airports in the world presents unique challenges, particularly maintaining day-to-day operations while managing massive construction efforts. The project employs over 5,000 workers, utilizing innovative construction methods such as prefabricated materials and modular construction techniques to minimize disruption. These methods not only expedite the building process, but also help manage the logistical complexities of working within an operational airport. The O'Hare expansion will also address some of the airport's long-standing issues, such as congestion both on the tarmac and inside the terminals. By redesigning gate layouts and improving the configuration of taxiways and runways, the project aims to significantly reduce taxi times and delays, thus solving a critical problem that has plagued O'Hare for decades.
Moving over to Chicago, we have to talk about the Lincoln Yards Megaproject. This expansive plan, spearheaded by Sterling Bay, is a $6 billion redevelopment plan that is reshaping over 55 acres of former industrial land into a vibrant, mixed-use complex. Upon its phased completion, with projections spanning the next decade, Lincoln Yards aims to serve as a new epicenter for residential living, commercial activity, and cultural flourish in Chicago. A pivotal element of Lincoln Yards is its promise to create upwards of 24,000 full-time jobs during its construction phases, involving a vast array of trades and specialties. At its core, Lincoln Yards is designed to address the pressing need for urban revitalization and connectivity between Chicago's northwestern neighborhoods, effectively bridging a gap that has long segmented the city. The development encompasses over 14 million square feet of buildings, including high-rise residential towers, office buildings, and an array of retail spaces. One of the major challenges Lincoln Yards faces is integrating this vast new development seamlessly with existing infrastructure. The plan includes substantial improvements to local transit systems and roadways, including a new metro train station, multiple new bridges over the Chicago River, and enhanced pedestrian and bike paths to ensure accessibility and reduce traffic congestion. An ambitious aspect of the Lincoln Yards project is the proposed Live Nation Entertainment District, which will include multiple venues for concerts and cultural events, capable of hosting thousands of visitors. This entertainment component is envisioned to be comparable in scale to London's O2 Arena district, albeit integrated within a larger mixed-use development.
But that's not even close to the most expensive project located in New York. Let's talk about the new Yankee Stadium, which opened its doors in 2009 in the Bronx. This modern cathedral of baseball came with a hefty price tag of approximately $3.3 billion, making it one of the most expensive sports venues ever built at the time. The stadium's design paid homage to the original 1923 Yankee Stadium, with its iconic facade and the replication of the original field dimensions. However, it introduced modern amenities and technology to enhance the fan experience. These included more than 50 luxury suites, high-definition video screens, and improved seating with greater legroom and sightlines. Did you know that the construction of the new Yankee Stadium required the demolition and redevelopment of Maccombs Dam Park? This aspect of the project added to its complexity and cost, as new recreational facilities had to be built to replace the parkland used for the stadium. The project's engineering efforts also addressed the challenge of building atop the New York City subway's elevated 4-train line, requiring careful planning to avoid disruptions. Let's go to the Louisiana offshore oil port, which stands as the only port in the United States capable of offloading deep draft tankers. Situated approximately 18 miles off the coast of Louisiana, the port plays a pivotal role in the import and export of crude oil, handling about 10 to 15% of the country's domestic oil. Built in 1970, the construction of this engineering feat was both a logistical and financial endeavor, costing over $300 million at the time, an amount equivalent to over $1.4 billion today when adjusted for inflation. Did you know that one of the most significant challenges during the port's construction was the laying of its underwater pipeline? This pipeline stretches over 48 miles to the onshore storage facilities and was one of the longest and most expensive underwater pipeline projects at the time. Next up, we have to discuss one of the most expensive megaprojects in the world, called the Hanford Nuclear Reservation Cleanup. Situated in Washington State, the Hanford site was once home to the largest plutonium production facility in the United States, playing a pivotal role during World War II and the Cold War. However, decades of nuclear production have left a legacy of contamination, necessitating an extensive cleanup effort with costs estimated to range between $300 billion and $600 billion. The Hanford Nuclear Reservation spans 586 square miles and includes 9 decommissioned nuclear reactors and numerous processing facilities. The cleanup project, managed by the U.S. Department of Energy, officially began in 1989 following the site's designation as a Superfund site by the Environmental Protection Agency. One of the primary challenges of the Hanford cleanup is dealing with the vast quantities of radioactive waste stored in underground tanks. These tanks, some of which are over 70 years old, have been found to leak, posing a significant threat to the surrounding environment. A critical component of the cleanup is the construction and operation of the waste treatment and immobilization plant, also known as the vitrification plant. This facility aims to convert radioactive waste into a stable glass form through a process known as vitrification. By immobilizing the waste in glass, the long-term risk of environmental contamination is significantly reduced. The plant is one of the most complex and expensive construction projects at Hanford, with an estimated cost of $17 billion. The cleanup efforts at Hanford also involve the remediation of contaminated soil and groundwater. Advanced technologies and methods, such as pump and treat systems, are employed to remove radioactive contaminants from groundwater and prevent their migration. The project has faced numerous challenges, including technical difficulties, regulatory hurdles, and budget constraints. Despite these challenges, significant progress has been made in reducing immediate risks and advancing long-term remediation goals. Comparatively, the Hanford cleanup is unparalleled in its scope and complexity, reflecting the immense legacy of the United States nuclear weapons program. The project's costs and duration are unprecedented, with estimates suggesting the cleanup could continue for several more decades. Next up, it's time to visit one of the most expensive hotels in the United States. The Cosmopolitan in Las Vegas presents a fascinating study in both engineering achievement and financial investment. Opened in December 2010, this resort and casino complex was developed at a staggering cost of approximately $5.3 billion, making it one of the most expensive hotel projects in the world. A unique aspect of the Cosmopolitan's construction is its vertical design, a necessity dictated by the limited space available on the Las Vegas Strip. Standing at nearly 600 feet tall, these towers house over 3,000 hotel rooms, alongside a vast array of amenities including a casino, retail spaces, restaurants, and entertainment venues. Did you know that the project faced financial challenges during its construction, largely due to the economic downturn in 2008? This led to changes in ownership and a significant injection of additional funds to complete the project. Moreover, the Cosmopolitan is renowned for its emphasis on art and aesthetic appeal, featuring a multi-million-dollar art collection and striking design elements like the digital columns in its lobby. It's time to talk about the construction of Raleigh Union Station. This transformative project, which officially opened its doors in July 2018, represents a major upgrade from the previous Amtrak station. Costing approximately $111.4 million, the Raleigh Union Station was meticulously designed to rejuvenate the warehouse district of downtown Raleigh, providing a multimodal hub that accommodates train, bus, and taxi services under one roof. Spanning a vast area of 26,000 square feet, the station's main building was once a dilapidated steel fabrication plant, which has been artfully transformed into a state-of-the-art facility while retaining historical architectural elements. This adaptive reuse not only preserves a piece of Raleigh's industrial heritage, but also incorporates green building practices, including a rooftop rainwater collection system that underscores the city's commitment to sustainability. The construction of Raleigh Union Station was a complex endeavor, involving numerous challenges ranging from the preservation of the existing historic structure to integrating advanced technological systems. The project team employed innovative construction methods such as seismic retrofitting to ensure the station's durability and safety, all while maintaining the integrity of the original building's rugged, industrial aesthetic. The station features lofty ceilings and a spacious concourse flooded with natural light, creating an inviting atmosphere for the approximately 160,000 passengers it serves annually. Raleigh Union Station is equipped with longer, high-level platforms that accommodate more passengers and improve the boarding process for Amtrak's Piedmont and Carolinian lines, as well as future high-speed rail services. Welcome to the Muskrat Falls Project, a colossal hydroelectric power station on the lower Churchill River in Labrador. Did you know that the Muskrat Falls project spans over 100 square kilometers? The project harnesses the power of water, generating up to 824 megawatts of electricity, enough to light up over 500,000 homes. Construction kicked off in 2013 and, amidst various challenges, wrapped up in late 2020. The scale of this endeavor is staggering, with a final cost soaring to approximately 12.7 billion Canadian dollars. Originally estimated at 7.4 billion, the financial scope ballooned due to unforeseen geological challenges and logistical complexities. The construction of the dam itself is a feat to behold. The main dam, made from over 2.2 million cubic meters of concrete, stretches across 32 meters in height and an impressive 432 meters in length. The project utilized innovative construction techniques, such as the extensive use of large-scale prefabricated modules to speed up the construction process and reduce the environmental impact. The harsh weather conditions of Labrador, with freezing temperatures and heavy snow, tested the mettle of every worker on site. Muskrat Falls also integrates cutting-edge technology with a series of 204-kilometer transmission lines, known as the Labrador Island Link, which connect the power generated from the falls to the population centers. This technological marvel includes software that allows the power flow to be adjusted in real time, optimizing energy distribution based on current demand and supply conditions. Muskrat Falls is connected to the island of Newfoundland by a subsea cable spanning nearly 30 kilometers across the seabed of the Strait of Belle Isle. This is one of the longest subsea electricity cables in the world, a little shorter than the length of Manhattan. But it's time for the next project on our list. In the heart of Manitoba lies the Kiesk Hydroelectric Project, a marvel of engineering nestled along the Nelson River. Construction of the Kiesk project commenced in 2014, with a projected completion date of 2021. However, like many ambitious undertakings, the journey was fraught with challenges. The final cost of the project soared to approximately $8.7 billion, nearly double the initial estimate. This escalation stemmed from various factors, including unforeseen geological obstacles and environmental mitigation efforts. Spanning an area of over 23 square kilometers, the dam reaches a height of 23 meters and stretches over 640 meters in length. The construction process required a workforce of over 6,000 individuals, comprising skilled laborers, engineers, and environmental experts. These dedicated individuals braved the harsh Manitoba winters and navigated complex logistical challenges to bring this project to fruition. One of the key challenges faced during construction was the need to mitigate environmental impact. The project team implemented innovative solutions, including the construction of fish passages to ensure the continuity of fish migration routes and the preservation of local ecosystems. The Kiesk project integrates advanced technology to optimize power generation and distribution. The hydroelectric station boasts 6 generating units, capable of producing a combined output of 695 megawatts, enough to power approximately 400,000 homes. The electricity generated is transmitted through a network of transmission lines, connecting remote northern communities to the provincial grid. The completion of the Kiyask hydroelectric project marks a significant milestone in Canada's pursuit of renewable energy. For the next project, journey with us into the heart of Toronto, where the Eglinton Crosstown Light Rail Transit Project is reshaping the city's transit landscape. Spanning an ambitious 19 kilometers across Eglinton Avenue, the project was initiated in 2011 and completed in 2022. The project, budgeted at approximately $12 billion, underscores an epic saga of urban development, involving over 10,000 workers at its peak construction phases. The LRT line includes a significant underground section, spanning about 10 kilometers. Constructing this section involved the use of tunnel boring machines, each 10 meters in diameter. The scale of excavation is immense, with the project moving enough soil to fill the Rogers Centre twice over. One of the project's major challenges has been managing construction while minimizing disruption to one of Toronto's busiest arteries. Advanced technologies and construction methods, such as the cut and cover and sequential excavation method, have been employed to ensure the structural integrity of the cityscape and the safety of its bustling populace. Each of the 25 stations on the line presents its own unique architectural and functional features, designed to not only accommodate but also enhance passenger experience with art installations and technology. This project also tackles the pressing issue of urban congestion. By providing a reliable and efficient alternative to road transport, the Eglinton Crosstown LRT is expected to serve around 5,500 passengers per hour in each direction during peak times. Facing its fair share of hurdles, from labor strikes to engineering challenges due to the city's complex underground infrastructure, the project has navigated through delays and budget overruns, reflecting the all-too-common tale of large-scale urban transit projects. For our next project, we have to step into the bustling heart of British Columbia, where the Vancouver International Airport expansion is located. Launched in 2017, this expansive project was completed in 2022 with a cost of around 9.1 billion Canadian dollars. It's designed to accommodate the soaring passenger numbers, which are expected to reach 25 million annually by the end of the decade. This scale of growth brings its set of challenges and innovations, making the airport a focal point of Canadian aviation development. One of the most intriguing aspects of the expansion is the addition of a new international terminal wing. Spanning the length of nearly 3 Canadian football fields, the new wing is being built to handle the largest aircraft in the world. With 8 new gates, this terminal is not just large, but also a marvel of sustainability, designed to meet LEED Gold standards. The project also includes a massive upgrade to the airport's baggage handling system, increasing its capacity by 75%. This system will integrate cutting-edge technology to speed up baggage processing and improve the overall passenger experience. Construction at an operational airport presents the unique challenge of maintaining daily operations while minimizing disruption to passengers. The team has navigated these challenges through meticulous planning and phased construction, allowing the airport to remain fully functional as a key international hub. Comparatively, the scale of the airport's expansion is akin to adding a whole new airport the size of London City Airport right within its existing footprint. It's time to investigate the LNG Canada project next, which is a venture set to transform not only the landscape, but also the energy dynamics of the region. Initiated with a vision to tap into Canada's vast reserves of natural gas, the LNG project commenced in 2018 with an anticipated operational start by 2020. The project's grand scale is reflected in its $40 billion budget, making it the largest private sector investment in Canadian history. The ambition here is to liquefy natural gas efficiently and transport it across the globe, positioning Canada as a key player in the global energy market. The construction site itself spans over 400 hectares, equivalent to around 560 soccer fields combined. At the heart of the project are the advanced facilities designed to liquefy natural gas by cooling it to -162 degrees Celsius, transforming it into a liquid to reduce its volume nearly 600 times, making it easier and safer to store and ship overseas. The project's construction team employs cutting-edge construction techniques, including modular construction where large components are prefabricated elsewhere and assembled on-site, reducing construction time and environmental impact. The project is designed to achieve the lowest carbon intensity of any large-scale LNG plant in the world, utilizing renewable hydroelectric power for some of its processes, a significant departure from the more common reliance on fossil fuels for such operations. Challenges have been plentiful, ranging from logistical issues in transporting massive equipment through rugged terrain to navigating stringent environmental regulations that govern the preservation of the pristine northern British Columbia environment. We have to travel over to Alberta next for the Trans Mountain Pipeline Expansion Project next. Launched in 2017, this monumental project is designed to twin the existing pipeline, increasing the capacity from 300,000 to 890,000 barrels of oil per day, ensuring Canada's position as a leader in the global oil market. Spanning a staggering 150 kilometers, this pipeline cuts through mountains and rivers, connecting Alberta's rich oil fields to the world. The scale is immense, involving thousands of workers, each dedicated to meticulously constructing a route that respects both the environment and the communities it passes through. With a budget now estimated at 12.6 billion Canadian dollars, the project's costs have escalated due to rigorous environmental safeguards and the strategic implementation of cutting-edge construction technologies designed to minimize ecological impact. These methods include horizontal directional drilling, a technique that allows the pipeline to pass beneath sensitive ecological areas and major obstacles like the Fraser River without disturbing the surface. But the journey has not been without its hurdles. Navigating through one of the world's most rugged terrains, the project faces the relentless challenge of mountainous landscapes and the strictest environmental scrutiny. The line must also withstand the threats posed by seismic activity, demanding that every segment of the pipeline not only meets but exceeds safety standards. The expansion is more than just an engineering feat. It solves the critical problem of landlocked Alberta's oil market access. By providing a direct link to the Pacific coast, it opens up lucrative Asian markets, potentially increasing Canada's GDP by billions of dollars and ensuring thousands of jobs for Canadians for years to come. In terms of sheer volume, the amount of steel used in the pipeline is equivalent to building 60 Eiffel Towers. Next up, it's time for the Cinder Block project located in Ottawa. This extensive project aims to extend the life of the building for another century while updating it to meet contemporary standards of safety, accessibility, and functionality. Spanning over 500,000 square feet, the Cinder Block's overhaul is one of the largest heritage restoration projects in the world. In terms of interior upgrades, approximately 6,500 windows are being restored or replaced, and all mechanical and electrical systems are being completely overhauled to include state-of-the-art heating and information technology networks. These updates are critical in a building that must remain operational 24/7 and secure. The restoration also includes the removal and preservation of about 20,000 individual pieces of historically significant stonework. Each stone is bar-coded and tracked for restoration and exact replacement, utilizing both traditional stonemasonry techniques and advanced robotic cutting technology. Adding to the complexity, a new visitor welcome center is being constructed, which involves excavating nearly 50,000 cubic meters of bedrock equivalent to about 20 Olympic swimming pools. The project is expected to cost up to 5 billion Canadian dollars, a figure that reflects both the complexity of the work and the value placed on preserving a key element of Canada's national heritage. Environmental sustainability is a core component, with the project targeting LEED Gold certification through the use of sustainable materials and practices, including the maximization of natural light and the installation of energy-efficient systems that will reduce the building's carbon footprint. Welcome to the Port Mann Bridge, a towering marvel that stitches the sky over the Fraser River in British Columbia. Stretching over 10 lanes, the bridge spans an impressive 65 meters in width, which is almost as wide as 2 Olympic-sized swimming pools laid side by side. At its completion in 2012, it claimed the title of the longest cable-stayed bridge in North America, with a main span reaching 470 meters. The project wasn't just about setting up concrete and steel. It involved a meticulously orchestrated ballet of high-stakes engineering and logistics. Over 4,000 workers, each playing a pivotal role from welding to the precision placement of the 288 cables that support the massive span. These cables, if laid end to end, would stretch over 45 kilometers. The bridge was built to replace an older 5-lane bridge, addressing both the growing traffic needs and improving safety. The old bridge was frequently a choke point, snarling traffic and causing headaches for commuters. This new architectural giant not only doubled the number of lanes, but was designed to stand up to seismic events, a critical feature in the earthquake-prone Pacific Rim. But like any massive project, the Port Mann Bridge faced its share of challenges. Construction took place in a busy urban area, requiring intricate planning to minimize disruptions. Moreover, the project faced environmental concerns, particularly with its impact on the Fraser River's delicate ecosystem. Innovative solutions were applied, such as extensive water monitoring and careful timing of construction phases to protect local wildlife, especially the salmon runs. The cost of the bridge itself was a hefty $3.3 billion, part of a larger $2.46 billion highway improvement project, making it one of the most expensive infrastructure undertakings in Canada. In comparison to other megaprojects around the world, the Port Mann Bridge is a standout for its width and its advanced cable-stayed design, a technique also used in the famous Millau Viaduct in France, albeit on a grander scale. Let's travel over to the next project, called the Evergreen Line. When the Evergreen Line opened its doors to the public in December 2016, it wasn't just unveiling a new set of tracks. It was laying down 11 kilometers of advanced rapid transit that now serves as a critical spine, connecting over 70,000 passengers daily. This $1.43 billion project showcases the sheer scale and ambition of modern infrastructure endeavors, employing state-of-the-art construction methods and technology. Constructing the Evergreen Line involved laying enough track to stretch across about 100 football fields placed end to end. Within this sprawling network, 6 new stations emerged, each designed with unique architectural elements reflecting the character of their respective neighborhoods, enhancing not just functionality but also community identity. The construction of this project was a monumental task involving more than 8,000 workers who came together to tackle a variety of complex challenges. One of the most significant feats was the boring of a 2-kilometer tunnel beneath Burnaby Mountain, a technical marvel in itself. This tunnel, crucial for connecting the two ends of the line, required one of the largest earth pressure balance tunnel boring machines used in North America. The machine, nicknamed Alice, represents the spirit of innovation and determination that fueled this project. Dealing with the diverse terrain of the region, from dense urban areas to the delicate ecosystems surrounding the mountain, posed its own set of challenges. Engineers and planners meticulously designed the route and construction phases to minimize environmental impact, which included preserving the local creeks and surrounding green spaces. It's time to investigate the Oak Ridge Centre redevelopment in Vancouver, British Columbia. Embarking on its journey in 2019, this megaproject is slated for completion in phases, culminating in 2025. It's not just a facelift, but a complete overhaul of the 1955-era shopping mall into a vibrant, mixed-use community space. The scope is a staggering $5 billion investment that promises to redefine luxury and accessibility in urban development. The Oak Ridge Centre isn't just growing, it's being reinvented, set to encompass over 2.7 million square feet of retail and residential space combined. That's about the size of 47 football fields. Within this sprawling complex, there will be over 2,600 homes housing approximately 6,000 residents. The building's design includes cutting-edge sustainability features aiming for LEED Gold certification, which involves sophisticated water recycling systems and energy-efficient building practices. But as with any project of this magnitude, challenges are part of the story. The redevelopment must intertwine with the existing metro line, demanding precision and innovation to ensure seamless integration without disrupting daily commuter flows. Moreover, balancing the needs of current tenants with ongoing construction activities requires a symphony of logistical prowess. Oak Ridge's planned retail space alone will rival the size of the famed Mall of America in terms of square footage. It's time to move over to the next megaproject. Welcome to the Vimy Memorial Bridge, an engineering marvel stretching gracefully over the Rideau River in Ottawa, Ontario. This bridge was opened to the public in 2014, embodying a blend of historical significance and modern engineering. Diving into the details, the bridge spans an impressive 125 meters with a width of 42 meters. Its construction was a sophisticated operation involving the precise placement of enormous precast concrete girders, each carefully lifted by a 100-ton crane. This method not only ensured the structural integrity, but also highlighted the advanced techniques used in its design. A project of this magnitude required a substantial investment, with the budget reaching around $50 million. This funding was directed into various aspects of the construction, ensuring that the bridge was built to last and to handle the heavy traffic flow efficiently. More than 300 skilled workers contributed to the project, working diligently to meet the construction deadline and tackle any challenges that arose. The environmental impact was a significant concern given the bridge's location over a navigable waterway. Stringent measures were taken to protect the Rideau River's water quality and its surrounding ecosystems. In terms of materials, the bridge required about 6,000 cubic meters of concrete and 4,000 metric tons of structural steel, all carefully selected to ensure durability and aesthetic appeal. These materials were crucial in constructing a bridge that was not only functional, but also visually striking. What sets the Vimy Memorial Bridge apart is not just its functionality, but its commemorative nature. The bridge features a dedication plaque that includes soil from the actual Vimy Ridge battlefield in France, making it a living memorial that honors Canadian history while serving a practical purpose in modern-day Ottawa. Let's move over to the Spadina subway extension megaproject next, located in Toronto. Officially opened in December 2017, this project not only extended the western reach of the city's subway network, but also bridged the gap between Toronto and the York region, fostering an unprecedented level of accessibility across these bustling areas. The extension added 6 new stations along an 8.6-kilometer stretch, starting from Downsview Park all the way to the Vaughan Metropolitan Centre. The design and construction of these stations involved a collaboration among some of the world's most innovative architects and engineers, aimed at creating spaces that are not just transit nodes, but also community hubs. The budget for this expansive project was initially set at $2.6 billion, but saw an increase to nearly $3.2 billion due to various challenges and complexities encountered during construction. These challenges included engineering hurdles such as tunneling near existing infrastructure, managing underground water flows, and coordinating with multiple contractors and stakeholders to keep the project moving forward smoothly. One of the most significant engineering feats was the use of tunnel boring machines, which carved through the earth beneath the city with precision. These machines played a pivotal role in creating the 6.4-kilometer twin tunnels that form the backbone of the extension. The project not only expanded the physical landscape of Toronto's subway system, but also addressed crucial urban issues like congestion and sustainable urban growth. By providing a reliable and efficient public transit option, the extension has significantly reduced traffic volumes on the busy highways and main roads, leading to a more environmentally friendly and less congested urban environment. But we haven't talked about the Regina Bypass megaproject yet. Officially opened in October 2019, this bypass is not just a road. It's the largest transportation infrastructure project in the province's history, designed to streamline traffic and foster economic growth by improving access to the global transportation network. Spanning an impressive 61 kilometers, the Regina Bypass circles the city, from Highway 11 west of Regina through to Highway 1 east, providing a vital link for the heavy flow of trucks and local traffic. The construction of this mega project involved laying hundreds of thousands of tons of asphalt, enough to cover a 2-lane road stretching from Regina to Moose Jaw and back again. With a budget of approximately $1.9 billion, the project marked a significant investment in Saskatchewan's infrastructure. The bypass features 12 overpasses, 40 kilometers of new 4-lane highway, and 20 kilometers of resurfaced 4-lane highway. It also includes 55 kilometers of new service roads, offering a comprehensive network that enhances connectivity for local communities. Over 2,000 workers were involved in the construction, applying their skills across various aspects of the project, from earth moving and paving to bridge construction. This workforce was crucial in managing the 11 million cubic meters of earth moved during construction, an amount that could fill 4 Empire State Buildings. The project employed innovative construction techniques, including the installation of wildlife crossings to maintain natural habitats and migration patterns. Additionally, advanced engineering solutions were necessary to build the bypass in the challenging prairie landscape, often dealing with extreme weather conditions that required robust planning and adaptation. The Regina bypass not only solves the problem of urban traffic congestion, but also significantly reduces travel time for freight transport, crucial for an agricultural hub like Regina. Special features of the project include innovative interchanges designed to handle large volumes of traffic efficiently, and the implementation of modern tolling technology to ensure ongoing maintenance and infrastructure funding without traditional toll booths. We have to move over to the Samuel de Champlain Bridge next. Spanning majestically over the St. Lawrence River, the bridge connects the island of Montreal with the South Shore in Quebec. This stunning piece of architecture, which officially opened in June 2019, stands as one of the largest infrastructure projects in North America and a pivotal gateway for the millions who traverse this corridor each year. The bridge stretches an impressive 3.4 kilometers in length, with a signature cable-stayed portion that reaches a height of 170 meters above the river. Designed not just for vehicular traffic, the bridge also accommodates a dedicated transit lane that will eventually support the REM light rail system. Building the Samuel de Champlain Bridge was a monumental endeavor, with a budget exceeding $4.4 billion. This project was essential to replace the aging original Champlain Bridge, which was one of Canada's busiest, carrying over 50 million vehicles annually. The old bridge was facing structural deterioration, posing a significant risk and necessitating the construction of a new, more durable structure. More than 2,000 workers were involved in the construction, utilizing innovative construction methods and materials to ensure longevity and durability. The bridge features a superstructure made from 74,000 tons of steel and 150,000 cubic meters of concrete. The construction faced significant challenges, particularly in managing the logistics of building in a busy urban area while minimizing disruptions to the existing traffic flows on the old bridge. Besides that, innovative techniques were employed to monitor and mitigate environmental impacts throughout construction. Comparatively, the scale and complexity of the Samuel de Champlain Bridge can be likened to San Francisco's Golden Gate Bridge in terms of iconic status and engineering marvel, though each unique in their structural expressions and utility. It's time to talk about the Quebec City Tramway project. This initiative reflects Quebec's commitment to sustainable mobility and is set to dramatically reshape how residents and tourists navigate the picturesque city. Projected to be operational by 2028, the tramway will stretch over 23 kilometers, featuring 23 stations and connecting major hubs like St. Foy and Charlesbourg to the heart of the old city. With a hefty budget estimated at over $3.3 billion, the tramway project is designed not only to enhance transportation, but to invigorate the local economy by improving accessibility to key commercial areas and reducing traffic congestion. The plan includes low-floor tram vehicles capable of enduring the city's challenging winter conditions, showcasing advanced engineering that prioritizes reliability and efficiency. Construction of the tramway involves laying tracks that will weave through densely populated neighborhoods and historic areas, requiring meticulous planning to preserve the integrity and heritage of the cityscape. This project is not without its problems. The construction phase has to address the city's unique topography and cold climate, which can significantly complicate excavation and construction activities. Special techniques are being used to minimize disruption to the daily lives of thousands of residents and to protect the architectural heritage for which Quebec City is famous. In terms of scale, the tramway's reach and impact are comparable to major transit projects like the Portland streetcar in Oregon, although Quebec's version is specifically tailored to meet the demands of a city known for its steep hills and historic architecture. The tramway will use a combination of at-grade and elevated tracks, strategically designed to blend with the surrounding environment while providing unobstructed views of the city's landmarks. Another innovative aspect of the Quebec City Tramway is its environmental focus. The project aims for a significant reduction in greenhouse gas emissions by promoting public transit over car use. The tram cars themselves are designed to be energy efficient and are expected to operate entirely on hydroelectric power, reflecting Quebec's abundant hydroelectric resources and commitment to renewable energy. The tramway is poised to solve several urban mobility issues, offering a reliable and eco-friendly alternative to car travel, thus enhancing the quality of life for residents and enriching the experience for tourists.
Hyperloop One is a groundbreaking transportation project set to revolutionize travel. Conceptualized by Elon Musk and currently under development by Virgin Hyperloop, this project aims to create a high-speed transit system using pods traveling through low-pressure tubes. The technology relies on magnetic levitation to eliminate friction and achieve speeds exceeding 600 miles per hour. Construction involves several critical components: the tube system, the pods, and the stations. The tubes are constructed from steel and reinforced concrete, designed to withstand external pressures and natural disasters. One of the engineering challenges is maintaining a near-vacuum environment inside the tubes to minimize air resistance. This requires advanced sealing techniques and constant monitoring to ensure the integrity of the system. The pods themselves are made from lightweight, durable materials like carbon fiber and aluminum. They feature aerodynamic designs to reduce drag and increase efficiency. Inside, the pods are equipped with comfortable seating, safety systems, and climate control to ensure a pleasant travel experience. Each pod is designed to be autonomous, with advanced navigation systems to manage speed, direction, and braking. Construction of Hyperloop One also includes the development of extensive infrastructure, such as power supply systems, control centers, and emergency response facilities. The power supply for the Hyperloop is primarily derived from renewable energy sources like solar panels installed along the tube's length. Control centers are crucial for managing the network, monitoring pod positions, tube pressure, and overall system health. In case of emergencies, the infrastructure includes rapid response teams and safety protocols to ensure passenger safety. One of the major construction challenges is the alignment and leveling of the tubes over long distances. Engineers use GPS technology and laser alignment systems to ensure the tubes are perfectly straight and level. This precision is essential to maintain the high speeds and safety standards of the Hyperloop. Additionally, constructing the system in various terrains, from urban environments to open countryside, requires adaptable construction techniques and materials. The Australia Pacific LNG project is one of the largest and most complex energy projects in the world. Located in Queensland, Australia, this project involves the extraction, processing, and transportation of natural gas from coal seams in the Surat and Bowen basins. The gas is then converted into liquefied natural gas for export to international markets. The project includes three main components: the gas fields, a 530-kilometer gas pipeline, and an LNG processing and export facility on Curtis Island. The construction of the gas fields involves drilling thousands of wells and installing extensive networks of gathering lines and processing facilities. These wells are drilled using advanced drilling techniques to reach deep coal seams and extract the gas. Hydraulic fracturing or fracking is employed to enhance gas flow, requiring precise control and monitoring to ensure environmental safety. The 530-kilometer gas pipeline is a critical component, transporting gas from the fields to the LNG facility. Constructing this pipeline involves trenching, welding, and laying pipes across diverse terrains, including forests, rivers, and farmland. Engineers use horizontal directional drilling to install the pipeline beneath major obstacles without disturbing the surface. This technique is particularly useful for crossing rivers and environmentally sensitive areas. The LNG processing facility on Curtis Island is where the gas is cooled to -260 degrees Fahrenheit, transforming it into a liquid state for easier transport. This facility comprises liquefaction trains, storage tanks, and loading jetties. Each liquefaction train involves complex engineering, with compressors, heat exchangers, and cryogenic piping systems working together to cool and liquefy the gas. The storage tanks are massive, double-walled structures designed to safely store the LNG at extremely low temperatures. One of the significant challenges of the Australia Pacific LNG project is the integration of its various components into a cohesive system. This requires meticulous planning, coordination, and execution to ensure all parts work seamlessly together. Additionally, the project must adhere to strict environmental and safety regulations, necessitating advanced monitoring and control systems to minimize environmental impact and ensure the safety of workers and surrounding communities. Moreover, the logistics of transporting such large volumes of natural gas require sophisticated shipping and handling facilities. The LNG is loaded onto specially designed carriers equipped with advanced containment systems to prevent leakage and ensure safety during transit. The Qatar Metro is an ambitious urban rail project designed to transform public transportation in Qatar. The metro system comprises 4 lines: red, green, gold, and blue, spanning a total of 300 kilometers and including over 100 stations. The construction of the Qatar Metro involves advanced tunneling techniques, station construction, and the installation of state-of-the-art train control systems. Tunneling for the metro lines employs tunnel boring machines, which are large, cylindrical machines that excavate and install tunnel segments simultaneously. These machines can operate 24/7, significantly speeding up the construction process. The tunnels are lined with precast concrete segments, which are assembled as the TBM advances. This method ensures the tunnels are structurally sound and resistant to groundwater ingress. Station construction involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. Additionally, the stations are equipped with advanced safety and ventilation systems to ensure passenger comfort and safety. The train control systems for the Qatar Metro are highly sophisticated, employing automated train operation technology. This system allows for driverless train operation, improving efficiency and reducing the risk of human error. The auto system is integrated with advanced signaling and communication systems, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the Qatar Metro project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the extreme weather conditions in Qatar, particularly the high temperatures, require special considerations for worker safety and construction materials. Furthermore, the project includes the development of a comprehensive support infrastructure, such as maintenance depots and control centers, to ensure the long-term operation and maintenance of the metro system. Patimban Port in Indonesia is a significant infrastructure project aimed at enhancing the country's maritime trade capacity. Located in West Java, the port includes a container terminal, car terminal, and supporting infrastructure. The construction of Patimban Port involves land reclamation, dredging, and the construction of extensive port facilities. Land reclamation is the first step, involving the creation of new land by dredging and filling the seabed with sand and rock. This process requires precise engineering to ensure the reclaimed land is stable and suitable for construction. Engineers use advanced geotechnical techniques to compact and reinforce the soil, preventing subsidence and ensuring long-term stability. Dredging is essential for creating deep water channels and berths to accommodate large vessels. This involves removing sediment and rock from the seabed using specialized dredging equipment. The dredged material is carefully managed to minimize environmental impact, and in some cases, it is used for land reclamation. The construction of port facilities includes building quays, warehouses, and support infrastructure. The quays are constructed using reinforced concrete piles driven deep into the seabed to provide a stable foundation. On top of these piles, concrete decks are cast to create the surface where cargo operations will take place. Warehouses and other buildings are constructed using steel frames and prefabricated panels, allowing for rapid assembly and scalability. One of the significant challenges of the Patimban Port project is managing the environmental impact of dredging and land reclamation. Engineers work closely with environmental experts to implement mitigation measures, such as creating artificial reefs and mangrove restoration projects to preserve marine habitats. Additionally, the project must adhere to strict safety and operational standards to ensure the port can handle the anticipated increase in maritime traffic. Moreover, the integration of advanced port management systems is crucial for optimizing cargo handling and logistics. These systems include automated cranes, real-time tracking, and inventory management tools to ensure efficient and timely operations. The Brasilia Digital TV Tower is a landmark structure in Brazil, designed by renowned architect Oscar Niemeyer. The tower stands at 600 feet tall and serves both as a broadcast facility and a tourist attraction. The construction of the tower involves advanced engineering techniques and careful architectural design to ensure its functionality and aesthetic appeal. The tower's foundation is a critical component, requiring deep piles driven into the ground to support the massive structure. These piles are typically made of reinforced concrete, providing the necessary strength and stability. The main structure is composed of a reinforced concrete core surrounded by a steel framework. This combination of materials ensures the tower is both strong and flexible, capable of withstanding wind loads and other environmental forces. One of the unique features of the Brasilia Digital TV Tower is its observation deck, located near the top of the structure. Constructing this deck involves installing large glass panels and steel supports to create a safe and accessible space for visitors. The deck provides panoramic views of the city, making it a popular tourist destination. The tower also houses advanced broadcasting equipment, including antennas and transmitters for digital TV signals. Installing this equipment requires precise engineering and coordination to ensure optimal signal strength and coverage. The equipment is housed in specially designed rooms within the tower, protected from environmental factors and easily accessible for maintenance. In addition to its technical functions, the Brasilia Digital TV Tower is an architectural masterpiece, embodying Niemeyer's vision of fluid, organic forms. The construction process required collaboration between engineers and architects to ensure the structure's aesthetic integrity while meeting functional requirements. The tower's sleek, modern design is a testament to Brazil's commitment to innovation and progress. The Napoli-Afragola rail station in Italy is a modern transportation hub designed to improve connectivity between Naples and other major Italian cities. The station, designed by architect Zaha Hadid, features a striking architectural design and advanced construction techniques. The station includes multiple levels, extensive platforms, and state-of-the-art passenger facilities. The construction of the station involves extensive earthworks, concrete pouring, and steel reinforcement to create a stable and durable structure. The platforms are designed to accommodate high-speed trains, requiring precise alignment and smooth surfaces to ensure safe and efficient operations. Engineers use advanced surveying and construction techniques to achieve the necessary precision. One of the significant challenges of the Napoli-Afragola rail station project is integrating the new station with existing rail infrastructure. This involves constructing new rail lines, switches, and signaling systems to ensure seamless connections with the existing network. Engineers use advanced computer modeling and simulation tools to plan and optimize the rail connections, minimizing disruptions to existing services. Additionally, the station's design incorporates numerous sustainability features, such as natural lighting, energy-efficient systems, and green spaces. These elements reduce the station's environmental impact and enhance passenger comfort. The station's construction also required meticulous planning to preserve the surrounding landscape and minimize disruption to local communities. Giga Berlin is Tesla's first European gigafactory, located in Brandenburg, Germany. This massive facility is designed to produce electric vehicles and batteries, significantly expanding Tesla's production capacity. The construction of Giga Berlin involves extensive site preparation, building construction, and the installation of advanced manufacturing equipment. Site preparation includes clearing and leveling the land, as well as installing utility infrastructure such as water, electricity, and sewage systems. This process requires careful planning and execution to ensure the site is ready for construction. The main buildings of Giga Berlin are constructed using prefabricated steel frames and panels, allowing for rapid assembly and scalability. These buildings include production lines, assembly areas, and administrative offices. The construction process involves extensive coordination between various contractors and suppliers to ensure all components are delivered and installed on time. One of the significant challenges of Giga Berlin is the installation of advanced manufacturing equipment. This equipment includes robotic assembly lines, battery production machines, and quality control systems. Installing and calibrating this equipment requires precision engineering and technical expertise to ensure optimal performance. Additionally, Giga Berlin incorporates numerous sustainability features, such as solar panels, rainwater harvesting systems, and energy-efficient HVAC systems. These elements reduce the facility's environmental impact and align with Tesla's commitment to sustainability. The construction also involves extensive collaboration with local authorities and communities to address concerns and ensure compliance with regulations. The Great Man-Made River Project in Libya is one of the largest and most ambitious water supply projects in the world. The project aims to transport water from underground aquifers in the southern desert to the coastal cities in the north. The construction involves digging massive tunnels, laying pipelines, and building pumping stations. The project includes over 1,750 miles of pipeline, making it one of the longest water supply networks in the world. Constructing these pipelines involves extensive excavation, welding, and laying of large-diameter pipes. The pipes are made from pre-stressed concrete, reinforced with steel to ensure durability and longevity. One of the significant challenges of the Great Man-Made River Project is managing the environmental impact and ensuring the sustainability of the water supply. Engineers must carefully monitor the aquifers to prevent overextraction and depletion of the water resources. Additionally, the construction process must adhere to strict environmental regulations to minimize disruption to the desert ecosystem. Moreover, the project's scale and complexity require advanced construction techniques and materials. The tunnels are constructed using tunnel boring machines, which excavate and reinforce the tunnel walls simultaneously. This method ensures the tunnels are structurally sound and minimizes disruption to the surface. The pumping stations are equipped with advanced pumps and control systems to manage the water flow and pressure throughout the network. Rail Baltica is a major infrastructure project aimed at integrating the Baltic states into the European rail network. The project involves constructing a new high-speed rail line connecting Estonia, Latvia, and Lithuania with Poland and the rest of Europe. The construction of Rail Baltica includes building new tracks, stations, and supporting infrastructure. Building the new tracks involves extensive earthworks, including excavation, grading, and laying ballast. The tracks are constructed using continuous welded rail, which provides a smoother and more reliable surface for high-speed trains. Engineers use advanced surveying and alignment techniques to ensure the tracks are straight and level, essential for maintaining high speeds and safety. The construction of stations and supporting infrastructure involves creating passenger facilities, platforms, and maintenance yards. These facilities are designed to be modern and accessible, providing a high level of comfort and convenience for passengers. Additionally, the project includes the installation of advanced signaling and communication systems to ensure safe and efficient train operations. One of the significant challenges of Rail Baltica is coordinating construction across multiple countries, each with its own regulations and standards. Engineers and planners must work closely with government authorities and stakeholders in each country to ensure the project meets all requirements and progresses smoothly. Furthermore, the project incorporates numerous sustainability features, such as energy-efficient systems, green infrastructure, and noise reduction measures. These elements reduce the environmental impact of the rail line and enhance the quality of life for communities along the route. The Incheon International Airport expansion in South Korea is a massive project aimed at increasing the airport's capacity and improving passenger services. The expansion includes the construction of a new terminal, additional runways, and supporting infrastructure. The new terminal, Terminal 2, is designed to handle 18 million passengers annually, increasing the airport's total capacity to 72 million passengers. Constructing the new terminal involves extensive earthworks, concrete pouring, and steel erection. The terminal is designed with a modern, open layout, featuring large glass windows and high ceilings to create a spacious and welcoming environment. Advanced construction techniques, such as prefabrication and modular construction, are used to speed up the building process and ensure high-quality finishes. The expansion also includes the construction of new runways, which involve extensive earthworks, grading, and paving. The runways are designed to accommodate the largest commercial aircraft, requiring precise engineering to ensure smooth and safe landings and takeoffs. One of the significant challenges of the Incheon International Airport expansion is managing construction activities while keeping the airport operational. Engineers and planners must carefully coordinate construction schedules and activities to minimize disruptions to airport operations and ensure the safety of passengers and workers. Additionally, the expansion incorporates numerous sustainability features, such as energy-efficient systems, green roofs, and rainwater harvesting. These elements reduce the environmental impact of the airport and enhance passenger comfort. The construction also involves extensive collaboration with local authorities and communities to address concerns and ensure compliance with regulations. São Paulo Metro Line 4 in Brazil is a critical infrastructure project designed to improve public transportation in one of the world's largest cities. The new metro line spans over 12 kilometers and includes 11 stations. The construction of Line 4 involves advanced tunneling techniques, station construction, and the installation of modern train control systems. Tunneling for the new line employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimizes disruption to the surface. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. The construction of stations involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. The installation of modern train control systems is essential for the efficient operation of Line 4. These systems include automated train operation technology, which allows for driverless train operation, improving efficiency and reducing the risk of human error. The auto system is integrated with advanced signaling and communication systems, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the São Paulo Metro Line 4 project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Furthermore, the project includes the development of a comprehensive support infrastructure, such as maintenance depots and control centers, to ensure the long-term operation and maintenance of the metro system. These facilities are equipped with advanced diagnostic and maintenance tools to ensure the reliability and safety of the trains and infrastructure. The Central Wan Chai Bypass in Hong Kong is a major infrastructure project designed to improve traffic flow and reduce congestion in the city. The project involves constructing a 4.5-kilometer-long highway, including a 3.7-kilometer tunnel connecting Central and Wan Chai. The construction of the bypass involves advanced tunneling techniques, extensive earthworks, and the installation of modern traffic management systems. Tunneling for the bypass employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimizes disruption to the surface. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. The construction of the highway involves extensive earthworks, including excavation, grading, and paving. The highway is designed to accommodate high traffic volumes, requiring precise engineering to ensure smooth and safe traffic flow. Additionally, the project includes the installation of modern traffic management systems, such as variable message signs and traffic cameras, to monitor and control traffic in real time. One of the significant challenges of the Central Wan Chai Bypass project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Moreover, the bypass incorporates numerous sustainability features, such as noise barriers, green walls, and energy-efficient lighting. These elements reduce the environmental impact of the highway and enhance the quality of life for nearby residents. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency. The Mersey Gateway Bridge in the United Kingdom is a major infrastructure project designed to improve connectivity and reduce congestion in the Merseyside region. The bridge spans 2 kilometers across the River Mersey, providing a new crossing between Runcorn and Widnes. The construction of the bridge involves advanced engineering techniques, extensive earthworks, and the installation of modern traffic management systems. The bridge is a cable-stayed structure, featuring 3 pylons and a series of cables supporting the bridge deck. Constructing the pylons involves driving deep foundations into the riverbed, using reinforced concrete to ensure stability and durability. The cables are made from high-strength steel, capable of supporting the weight of the bridge deck and the traffic it carries. One of the significant challenges of the Mersey Gateway Bridge project is managing construction in a tidal river environment. Engineers must carefully plan and execute construction activities to minimize disruption to river traffic and ensure the safety of workers and the environment. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. The bridge incorporates numerous sustainability features, such as energy-efficient lighting, stormwater management systems, and green spaces. These elements reduce the environmental impact of the bridge and enhance the quality of life for nearby residents. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency. The Rogfast Tunnel in Norway is a major infrastructure project designed to improve connectivity between the cities of Stavanger and Bergen. The tunnel, once completed, will be the longest and deepest undersea road tunnel in the world, spanning 27 kilometers and reaching depths of 390 meters below sea level. The construction of the Rogfast Tunnel involves advanced tunneling techniques, extensive earthworks, and the installation of modern traffic management systems. Tunneling for the Rogfast project employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimizes disruption to the surface. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. One of the significant challenges of the Rogfast Tunnel project is managing construction in a deep undersea environment. Engineers must carefully plan and execute construction activities to ensure the safety of workers and the structural integrity of the tunnel. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Moreover, the tunnel incorporates numerous sustainability features, such as energy-efficient lighting, ventilation systems, and emergency response facilities. These elements ensure the safety and comfort of tunnel users and reduce the environmental impact of the project. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency.